Ooh. No worries. Yeah, so I want to thank you all for coming as well. In a way, I was hoping for a smaller crowd today because it's been a long week as well. I'm very tired. I picked up an American virus, which seems to be a bit stronger than the New Zealand ones we get, so I apologise in advance if I'm a bit fluffy today. But yeah, it's so great to see so many people. I'd never get a crowd like this in New Zealand or Australia, so thanks again. Yeah. All right, so a little about me slide. I'm not going to dwell on this too much because, I'm kind of standing here so you can see me. I blog at sqlblog.com. If you haven't visited that site, you probably should. There's a lot of great content there from a lot of people. I know when I first got into SQL, SQL Blog was one of the places I used to go to read about fun stuff, with Kalen Delaney and Aaron Bertrand and Hugo Cornelis and all sorts of people that really helped me get into the internals of SQL Server. I'm on Twitter if you want to follow me or tweet me or anything else like that. I've got an underscore in my name on Twitter, so it's SQL_Kiwi, not the other guy. The account without the underscore isn't actually in use, but you won't get too much value if you follow that one. I'm just saying. Email SQLKiwi without the underscore at gmail.com. I'm always happy to receive emails from people so long as you're not inviting me to buy Nigerian bonds in something or other. No, seriously, if I get time, I'll always try and respond to people. Yeah, little picture of New Zealand. That's where I'm from. That's where I live. I'm an MVP currently, which I'm very grateful for a couple of years now. And the last little icon there, I want to give a shout out to one of the Stack Exchange sites, database administrators. It's dba.stackexchange.com. It's a great place if you have, especially an advanced SQL question, and not just SQL Server either, Oracle, MySQL, Postgres, all the others. It's a great site. If you can ask a good question, there are lots of really deep experts there. I hang out there as well, and we love to answer good questions. Okay, so that's about me. What we're going to talk about today, I want to set the scene a little bit with the first couple of slides. So we have SQL as our programming language, and SQL has its origins in set theory and in the relational algebra. So you'll look like a smart bunch of people. You'll know all about relational algebra and Dr. Cod and primary keys and foreign keys and relations and tuples and things like that. But that's where SQL's come from. It gets a lot of criticism for not being fully relational, but it's what we've got, so we have to kind of work with it, right? It's a declarative language, so for people that are used to coding in VB or C# or something else like that, you've got a pretty direct relationship between what you write and what the program does, how it's implemented. With SQL, it's a lot more abstract. So a lot of people that are new to SQL in particular don't really appreciate what they're writing with a SQL query is something that describes what they want. It doesn't say how to get it. It's just a way of describing the results that you want to see. And a lot of people really don't get that. I want to talk about the logical binding order because ITSEC talks about this, and it's in Books Online. If you look under the select statement in Books Online, it talks about a processing order. So again, people new to SQL often see this list, and they see, the from clause is processed first, then the on clause, then the join, and the where, group by, so on and so forth. You've all seen this, right? Yeah. Well, up until the R2 release of Books Online, it said nothing except that's how things were processed. And of course, that's just a logical order. That's the order in which things are bound. So the select clause, right down there towards the bottom, can refer to things defined in previous clauses. That's a binding order thing. It doesn't say that that's the order in which SQL Server is physically going to process the SQL you write. And again, this is a huge thing. I'm sorry if this is obvious, but I come across so many people that don't get this distinction between a logical query specification and a physical execution plan. Okay, the other thing about SQL is it deals with bags, or which are sometimes called multi-sets rather than pure sets. So a pure set only has distinct members, so you might have 1, 2, 3, 4, but a multi-set or a bag would have 1, 1, 2, 2, 2, 3, 4, 4, 4, 4, okay? So SQL departs from set theory, at least on that basis, and we can talk about nulls and three-valued logic and all the other funny, quirky things about SQL. Actually, before I go on, funny, quirky things about SQL, if anyone can explain to me later on why the sum of an empty set is null and not 0, I'd be happy to learn that from you. That's the quirk of SQL I've never understood. Sorry, excuse me. So SQL Server has an execution engine, which you can think of as just a bunch of generic modules that know how to manipulate data. So there's a physical filter operator that knows how to filter rows. It receives a stream of rows, it checks some predicate, some condition, and it passes the rows on that meet that condition. It's not aware of which query it's running in. It's a physical operator. It knows its job and it does it well. There's another physical operator for sort and a physical operator for hash join and things like that. So there's all these individual modular components in the execution engine, and they exist. Sorry, I didn't really know how to finish that sentence. Okay, so these components are iterators, which means they operate on one thing at a time in general. Okay, so one thing, again, that a lot of people don't appreciate is that the execution engine and the execution plans that you see are, generally speaking, cursors. Okay, so cursors have a bad name, and say don't use cursors, and I agree with that in general. Don't use T-SQL cursors. But the engine itself is engineered in such a way that iterators consume a row, they pull a row from their row source, they do whatever they're supposed to do with it in general, and they may or may not pass it on. And this is a row-by-row thing. Okay? You all look very offended that I just called the engine a cursor engine. But it's true, it's true. So they consume and generate a stream of data, or data. So, and the data flow in an execution tree or an execution plan is demand-driven. So the execution starts at the far left side of the plan. That's the first iterator to run, and it says, I need results for this query. I demand data. So consumers, by demanding data from their children in the tree, their producers, they cause producers to do the work that eventually produces the results you need. So it's a row-by-row thing. The thing at the root of the plan says, give me a row. The thing below it says, okay, I'll get you a row. Oh, hang on. I'll talk to my child to get you a row, and eventually it'll end up with something like a table scanner or a seek that has a row, and it passes that back up the tree. Now, the effect of all this is that data appears to flow right to left, right? Which for some reason people find very natural when reading query plans. They read right to left, whereas I read books left to right. I don't know, maybe that's just me. But people find it more natural to read right to left. And that's fine, I have no issue with that. If you're following the data flow and you're looking at general performance stuff, for sure, data flows right to left. But it's because iterators are demanding row by row from the left side of the query plan. Okay? Look skeptical, it's true. Okay, so we've got this execution engine. And iterators in the execution engine are either pipelined or stop and go or blocking. I think I prefer the word blocking, but internally it's called stop and go. So a pipelined iterator is something like a filter. It only needs one row on its input before it can decide whether to pass that on to its output or not. A sort, for example, is a blocking or stop and go iterator because it needs to consume its entire input before it can decide what the first row it needs to pass on its output is. Yeah, that makes sense, right? Okay. So then we have the optimizer, and the optimizer's job is to bridge these two things. And there's this big gap between declarative SQL and the execution engine. I talked about C#, the source code being very close to the executable binary that it produces. The distance is much, much bigger with SQL. You have a declarative bit of SQL that says, this is the shape of the results that I want, and the optimizer has to somehow turn that abstract, arbitrarily complex text into some combination of physical execution engine iterators in the right order to produce those results correctly under all circumstances. Okay? And ideally, the optimizer will produce exactly the same results. In fact, it has to produce exactly the same results as the declarative query said it should, but with any luck, it will do it with much greater efficiency. And that's the other difference between SQL and say, .NET languages. If the optimizer does a good job in a .NET language, you might get a 10 times or 100 times speed up. If the SQL optimizer does a good job, you might get a 10,000 times speed up. If it does a bad job, your query might run for weeks instead of seconds. So it's a big gamble. Okay. Alrighty. Another quick overview before we get into the deeper stuff. So this is one of the pictures of the SQL Server core engine that I like to keep in my mind. I've ripped it off pretty shamelessly from one of Kalen's books, SQL Server Internals 2008. I just like this diagram. I've coloured it myself though. Yeah, thanks. It took a while. It is. It's an underrated skill. Sorry? I did give her credit. I remembered this time. I didn't once, and I think I was going to get sued. But I hear Kalen's very nice, so yeah, not too worried. All right, so at the bottom in red we have SQL OS, which is SQL Server's OS-like services, provides threads and memory management and scheduling and all those good things, provides the cooperative scheduling model that makes SQL Server scale so well. Above that we have the storage engine, which I'm not really going to talk about too much today because I'm not Paul Randall, I'm Paul White. But the storage engine does things like transactions and locking and getting data from tables and all sorts of good things like that. Now above that we have the things that interest me most. Everything above the storage engine on that diagram used to be known as the relational engine. And this word relational, I've mentioned it a few times, it's going to come up today. I tend to bang on about being relational in general, and today is going to be no exception to that. It's good to be relational and know relational theory. Yeah, so above the storage engine, those three components used to be known as the relational engine. I thought that was a great name. These days it seems to be called the query processor. Yeah, okay. So we have the query optimizer, which is my favorite bit really. We have the query executor, which is the thing that actually physically runs the binary in the end of these iterators all connected together to produce your results. And above that we have this general thing called language processing execution. So in terms of a query arriving at SQL Server, the query arrives, it gets parsed to make sure it's syntactically correct, that sort of thing, bound to real objects, real object IDs and things in a database. The algebraizer has a go, sorts out what the group bys mean, which aggregates bind where, and all sorts of fun stuff like that. Not going to talk too much about that today. Then we optimize, which is the stuff we're interested in. And finally, we execute the query. And it's all color-coded there for your easy reference. Again, you're welcome. Okay. Now, this is the main diagram that I'm going to follow for the first sort of hour or so. This is the high-level optimization pipeline. Oh, by the way, I'm sorry if my wandering around the stage distracts you. It's my nerves, I just end up doing it, so I apologize, but that's the way it is. So the general pipeline is we have an input tree of logical operators, then we go through a process of simplification, we derive cardinality, the number of expected rows, that sort of thing, see if we can produce a trivial plan, go through cost-based optimization and exploration, and finally produce, hopefully, an awesome executable plan at the end of it. Now, I've rushed over that because I'm going to go into each of those in a bit more detail. Now, that's still a very high-level overview. The optimizer is a very, very complex product. There's a lot of code in there, as far as I can tell. So behind the scenes, there are all sorts of exciting things. If we had a full day, or maybe a full week, and maybe if I knew more details than I actually do, we could talk about this for a long, long time. So parsing, algebraizing, expanding views. I suppose expanding views is an important one. Again, a lot of people miss the fact that when you define a view and reference it in your query, that view is actually inlined into the query before the optimizer even sees it. So if you write the view, if you copy and paste the view text into your query and then optimize it, it's exactly the same. There is no difference than if you reference the view in your SQL. And again, it's something that a lot of people don't realize. Then there's a few stages like the beautifully named NNF convert, which is just about converting the tree into a format that the optimizer likes to work with. Okay, it's about normalizing ands and ors and things like that. But anyway, there is a lot more detail, but hopefully we can keep it relatively simple and understandable today. Okay. So the first stage after the parsing and algebraizing is we get this thing called a bound tree. So I have a little example query here, and of course I've based it on AdventureWorks because that's the only database I've got. So this is a real simple query, joining product to product inventory. And it's saying, okay, for all the products that we have that have a name that starts with the letters A through G, how many do we have in stock? Okay, pretty simple query. But I'm going to refer to this query a bit, so if you can kind of keep that idea of names through A to G and the sum of the quantity in stock, that's what we're looking for here. Okay. So the bound logical tree looks a bit like this in graphical form. And again, this is based on relational concepts and algebra for the most part. So at the bottom of the tree we have a relational get operation, which is logically reading the entire table. Okay, so we have a get from product and a get from inventory. Then we have a join, which in this case is a Cartesian product. You're not loving this query plan so far. Then we have a select, which is a relational select, not a SQL select. So relational select is sometimes called restrict. It's a filter, essentially, but they call it selection. Yeah, it's confusing, but that's how it is. Then above that we have a group by aggregate, which is grouping by name and computing the sum of the quantity. And finally we project out another relational term, just the columns that we need in the results set. Okay, so it's just a logical description of the query. Does that make intuitive sense to most people? Yeah, please raise your hand if anything strikes you as odd. So taking this logical query form, we then throw this at the optimizer, and it produces some awesome execution plan. With luck. It doesn't always. We'll talk a bit more about that later on. Okay. Now, I don't necessarily expect you to take my word for this, so I'm just going to demo the bound tree very quickly. And I didn't do any demos the other day because I didn't want to risk it, but I'm feeling braver today. So, with any luck, yeah, here we go. Can you see that okay? Sweet. So I'm using AdventureWorks 2012. No particular reason for that. It works on all versions of AdventureWorks, and these scripts will be available for download. I'll probably put it on my blog as well, but it should be on the PASS site later. So all these scripts are going to start off just by clearing the plan cache, and then turning on trace flag 3604. It's a pretty well-known trace flag, right? Just outputs certain messages to the Messages tab in Management Studio rather than writing it anywhere or not displaying it at all. So I'm just going to run that quickly. Okay, and this is our test query here. So it produces a list of products with names that start A through G with some total number that are in stock, and that's great. I don't know whether you noticed, but in the query I showed you before, I used the ANSI or ISO 89 syntax. So I didn't use the join syntax. I used commas and put the join predicate in the where clause. It's not something I generally do, but I wanted to show you a little difference. So by recompiling that query and using an undocumented trace flag, it's pretty well known again. A few people have blogged about it. Ben Navarro is sitting here. I know he's blogged about it. A guy called Dima Piliugin, I'm going to say, from Russia. He's blogged about it as well. 8605 is one of these trace flags that the optimizers, the developers, they put these trace flags in while they're working on the product and debugging it, and then they forget to take it out, which is great for us. And Microsoft really don't mind us using it. I asked Bob Ward the other night, and he said, yeah, no, that's fine. Just don't expect it to be supported or anything. Don't use it in production, that sort of thing. But if you just want to use these things to explore the behavior of the product, that's great. Okay? So query trace on is just another little undocumented thing to turn a trace flag on at the beginning of the query and turn it back off at the end. So I'm going to run this query now with this trace flag on. I'm going to run this query with the trace flag on. We'll get the same results. But in the messages pane, we now have a converted tree, which is essentially the same diagram I just showed you in colored form. So at the top of the tree, we have a logical operation, which is a projecting out the two columns, name and a computed expression labeled expression 1004. Below that, we have a gbag. Below that, a project and a select and a join. So it's the same tree, and I just wanted to prove to you that at this stage of processing, there really is a logical tree derived from the query text. Okay? All happy? Wave and smile if you like. Okay. So, having demoed that, the thing I wanted to point out on this particular page is that I wish I was better at Zoom it than I am. I might risk it later. The join has below it two logical gets, and then below that it has a logical and a compare equal on the product ID columns. So it really is doing a Cartesian product and then doing a comparison on each row to see if they joined or not. Okay? So the query syntax has had a small effect on the bound tree here. If I run the same query using the more modern syntax, I mean, the other one's fine if you prefer it. I don't. It's not deprecated or anything. You're free to use it. But using the join on syntax instead, again, same results, but and a very, very similar tree. But in this case, the scalar operator for comparing equal on product ID equals product ID is directly attached to the join. Okay, so there's not actually a Cartesian product in this case, but it's just a slightly different thing. Of course, logically expresses the same requirement. Okay, there's no logical difference here, but the tree is slightly different. Alrighty. Now, one thing I noticed when I was running this query is that the plan doesn't look very much like the query text that I gave it. The aggregate seems to be in the wrong place. I thought we were doing the aggregation last. We would join the tables and then do the aggregation. There's a merge join there for some reason. And I happen to know there's a non-clustered index on the name column on the products table. And I would have thought, with selecting just the names that began with A through G, that it would use that index. And I thought, well, perhaps I know better than the optimizer. I'm going to force the use of that index. So it's the same query, but with the AK product name index forced. And by the way, the previous query had an estimated cost of 0.029 mysterious optimizer units. They don't mean anything. They used to mean something. I'm sure everyone knows that story, right? There was a guy on the query processor team, and he had a machine. What was his name? Nick or something? And originally, the cost units were the number of seconds on his machine. And this was like, I don't know, 10 years ago or something. So it means nothing these days. But it's just a model. That's the way to look at it. So if you hover over the select icon in a Management Studio plan, slightly different in Plan Explorer, you see an estimated subtree cost. And that's the cost of the whole tree that the optimizer is estimated. And I hope you can see there. I'm gonna try and zoom it. Okay, hold your breath. Oh yeah, there you go. Thank you. That's settled the nerves nicely. Control 2. So estimated subtree cost of 0.029. Now, obviously, this isn't a very expensive query because it's AdventureWorks and I'm just playing around. But so that's the estimated cost of running the entire plan. Yeah, everyone knows. Yeah, the subtree cost includes everything below it in the tree. All right, awesome. So, but again, I wanted to use my index. I created this index for a reason. A through G should be reasonably selective. So here's my query again with the index forced. So I've got my seek. I was looking for index seek on my index, but now it's introduced a sort operator. And I'm thinking, oh, right, yeah. Because, of course, because the records from the non-clustered index seek on product name will come back, generally speaking, in product name order, right? And the merge join needs sorted input. So it wants both of its inputs sorted on the same key. And the join predicate is product ID equals product ID. So those strings need to be sorted by product ID and not by product name. So to fix that, given my query hint, it's had to introduce an explicit sort. Now, oh no. That's control 1. There we go. So my tuning efforts have resulted in a net drop of performance. It's now costed higher at 0.031, which is worse. Go me. Yeah. You come to see this guy. He makes execution plans slower. But I'm not ready to give up, because there's a merge join in that plan, and I know merge join has sorted inputs, and it also produces sorted output, generally. I mean, I haven't specified an order by clause, so it's not guaranteed, but I'm kind of expecting it to. But there's no requirement for that. I haven't asked them to come back in any particular order. I'm flexible. I just want the results. I don't care. So I'm going to insist. You stay with my index hint. But I want you to use a hash join, because I know that hash join, it's a pretty effective physical join algorithm. Doesn't produce sorted results. This plan will be a winner. I'm sure of it. Yeah, it looks simpler. Yeah, it looks good, right? Not convinced. Okay. Yeah, it's a lot worse. 0.034. Okay. So the message here, basically, what I'm trying to get across is that the optimizer has thought about this a bit. Okay. Okay, only in terms of its own model of costing. And in reality, one of my tuning efforts might run quicker in practice than it thinks. But generally speaking, it's thought about these ideas. Oh, I could use that index, but then I'd have to sort. Yeah, I could use a hash join, but a hash join means allocating some memory for hash buffers and doing some other things. So it comes out with a slightly higher cost. So at that point, I gave up and I thought, well, okay, we'll go with the optimizer's plan. It seems to know what it's doing in this case. Now, when I'm talking about input trees, I want to address another little thing that I see quite often. Common table expressions. Really, really badly described in books online, I think. It says something about a named temporary result set, yeah? Which makes people think, oh, this is a handy way to declare a table variable or a temporary table or something. If I put something in a CTE, that means it's going to get evaluated first and stored somewhere and then potentially reused or something like that. But they're not. It's just an inline view declaration, and it's expanded into the query text just like I talked about with views earlier. And I'm going to prove that to you in case it doesn't sound convincing. So there's a DMV called sysdm exec query optimizer info. It's documented and supported, and it has a number of counters in there that count up how many things the optimizer has done. And one of those is the number of view references that it's encountered and expanded. Okay? So at the moment on my system, that counter is 1342. So if I write the query slightly differently, with a common table expression just to fetch the products named A through G, and then reference that in the main outer query, we'll see in 8605 the trace flag is on. So on the Messages tab, you should see this guy here. You see the log-op view anchor? Okay, it's a logical operation. It's an anchor for a view definition. A view has been inlined into the query tree at that point in the plan. CTEs are views, inline views. Okay. And in case there's any doubt in your mind, I'm going to run that and look at the counter before and after I execute it. Okay, so 1345, results as I expect, and then 1346. Common table expressions of views, people. Did anyone have any doubts over that? Is that news to anyone? Oh, a question. Hello.
How about nested views or nested CTEs? Are they also expanded?
Sorry, could you ask that again?
Nested views, a view inside a view.
Right. So the question is whether nested views are expanded as well, and the answer is yes, absolutely. Yeah, so views inside of views inside of views, the whole thing gets expanded, and then optimized as a whole.
And optimizer on it.
Yep. Yep. Thank you, though. Good question. Now, if I'd written the same thing with a derived table, which, logically you'd think that's pretty similar to a common table expression. So it's exactly the same query again, but instead of using a CTE, I've used a derived table to find my products A through G. Again, same results, but my view reference counter hasn't changed. Derived tables are not treated as an inline view. Okay. That's the bound tree demo. Okay, so we've got a bound input tree. The first real stage of optimization is simplification. So it has this bound tree as its input, and it can do a bunch of tricks that are, generally speaking, regarded as always a productive thing to do. One of those is constant folding. So if you have an expression in your query like 10 times 5, a compilation time, it will evaluate that and inline the value as 50. And it works with more complex expressions than that as well, constant folding. We also, the product performs predicate pushdown. So if there's a filter further up the tree, it'll try and push it as close to the logical get operations as it can. The thinking is that it's always good to filter early if you can. If you reduce the row count earlier on, then iterators later on in the tree have potentially less work to do. It's also very useful for computed column and index matching. So if you have an expression in your query and a filter on it, and there's a matching definition on a computed column in the table, pushing that filter closer to the logical get makes it much easier to match those two things together. So if you've got an index on a computed column, that's the way the optimizer manages to match an arbitrary expression in your query to a computed column in the table. And it also helps with the generation of automatic statistics on computed columns as well. Now, this was introduced, I think, in 2005, this index and computed column matching thing. And it does have one side effect, which means that, which some people object to, which means that scalar expressions might be evaluated earlier than you might think from your query text. So maybe you perform a join or something that eliminates some rows, so you know you're only going to get stuff where it's safe to do a cast to integer or something. Maybe you're doing it on a string column, but you're filtering out on isNumeric or something like that. But the way it works means that the isNumeric might be called, so that some operation might occur before the isNumeric has filtered it out. This is where people rely on the logical order of processing, and they write an expression that's not safe if the optimizer decides to push this predicate and evaluate it earlier on. So in general, the optimizer doesn't make any guarantees about when it's going to evaluate a predicate or how often. Okay? It's just something good to know. The other thing simplification does is to rewrite subqueries. If you've got a subquery in your query text, it'll try and convert that to a logically equivalent join or an apply, which is just a correlated join. In some circumstances, if it's a subquery in the select clause, it might also rewrite it as an outer join, possibly with a group Bryan projection. I mentioned earlier that SQL has these little quirks about duplicates and things like that. So a lot of the optimizer is based on relational logic, which works on sets. So there are sometimes some little considerations it has to take into account because it has to preserve the number of duplicates and things. So it can transform things around, rewrite it as a join, but it has to be very careful to always produce the same number of duplicates, to eliminate nulls or not to eliminate nulls, which isn't strictly in the relational algebra, but the optimizer needs to make sure the results are still correct. Okay? So I think the worst thing you can do from the optimizer point of view is to produce results that are incorrect. It's all very good getting the results faster, but you do kind of want them to be right. The other very useful thing simplification could do is turn an outer join that you specified into a join. Most common case there is you've specified an outer join, and later on in the where clause you reject any nulls that might have been introduced by that outer join. So logically that's an inner join, and simplification can rewrite that for you. It can also remove any redundant joins in your query. Now you might say, well, this is ridiculous. I mean, I don't write queries with redundant joins in or outer joins, whatever. But lots of tools do. Okay, lots of ORMs and things that produce wacky-looking SQL. Simplification is there to get rid of the things that would otherwise make the optimization process much harder than it needs to be. Rob Farley, I don't know, is he here today? Is there a Rob Farley in the room? No, some people from Rob Farley's organisation. He did a great talk one year on the power of simplification to simplify joins and things. He's got a couple of blog entries as well. It's a very powerful thing, and I'll touch on it a little bit in a demo in a moment. And the final thing for simplification, it does contradiction detection. So if you have select star from product where 1 equals 2, logically that's going to produce no rows, right? That's a contradiction. And the optimizer can spot this with check constraints, and it looks at the whole tree, and it can find contradictions. And as I say, you don't write contradictions in your query typically, but there can be little areas of the subtree that, because of check constraints and some runtime parameter value, they can be safely eliminated, and it can throw that whole part of the tree away without affecting the results. Okay, good. And likewise, it can remove any expression or table that is provably empty at compilation time. Now, simplification is an all or nothing process. It's not cost-based optimization. It's not the fancy stuff that we're going to talk about later. Simplification is stuff that is regarded as always a good thing to do to a query tree, a logical query tree. It either applies a particular simplification or it doesn't. And it's a linear process as well. So simplification 1 gets applied, and then 2, and then 3. The intermediate stages aren't kept around. All right? So if a simplification applies, it applies, and that's the tree that moves on. There can be only one. It's a sort of Highlander thing. Think of simplification in a kilt, if it helps. Yeah. Oh, by the way, congrats to everyone who wore kilts yesterday. That was awesome. I would have done that, but I haven't got the legs for it. Okay. Now, as a demonstration of how powerful simplification can be, I do not expect you to be able to read the text on this query. Okay, but it's a complex common table expression that does 3 full joins. It projects all sort of columns out. And then there's a select on the end that says, from that CTE, give me the product name and the product ID from that complex query where the product name is like G. So it begins with a G. Now, the application of simplification, it can reason about integrity constraints, like foreign keys and things. It can reason about check constraints and all the other good things. And just by applying those simple rules that are always good, the query plan that comes out for that query is that. And that's awesome, right? And practically, I encourage you to track down Rob Farley's talk at SQLBits or one of his blog posts, because he uses that all the time in things like working with dynamics and other things, where very general views are specified by the system, and you write queries, and simplification really, really helps in those scenarios if you engineer it correctly. I think that's a very dramatic result. Very clever optimizer. Oh, he does. That's true. Thank you. Yeah, the comment there was that Rob's got a chapter in the first MVP deep dives on simplification. Yeah, buy that book. The proceeds go to War Child, is it? Yeah. If you haven't got a copy already, buy one. If you've got a copy, buy another one. Yeah. You should know the importance of backups, right? I get funnier as I get more relaxed. Okay, demo 2. Oh, beg your pardon. I mustn't do that. Demo 2 is simplification. Okay, so my usual precursor stuff, AdventureWorks 2012, get connected. All right, so here's a straightforward seek on the product table using a constant. And as you'd expect, this plan produces a nice, simple clustered index seek, and there's a seek predicate there saying product ID is less than 30. Awesome. We fully expect that to happen. Constant folding. I talked about evaluating a constant expression early. This one says, give me the products where its name is like substring left char ASCII char 68. Now, char 68 happens to be the character D, and then it gets a percentage sign added to it. And if we look at the execution plan for this wacky query, we find it's just an index seek. It's just an index seek. And I'm going to push my luck here. There you go. Go. Okay, so the seek predicate is saying from D, so greater than or equal to D and less than E. So it evaluated that expression early, turned it into a seekable range, and then it applies a residual predicate to make sure that it actually does match D%. Okay? Alrighty. Constant folding. Simplification can also remove redundancies, as I think I mentioned. So this is a query that says, give me all the information you have on product ID 400. And that's nested inside a query that says, yeah, where product ID is 400, where product ID is 400, where product ID is 400. Again, you do not write queries like this. I don't write queries like this, but yeah, NHibernate does. All right. So with simplification, I mean, you joked there was a query submitted to a mailing list the other day, I think, and it was just mind-blowing. It had where bracket, 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 null is null, close bracket, or, you know, fantastic thing it generated. Who'd be an optimizer, right? I mean, that's just rubbish. Okay, so the simplification process has seen through all that, and it's just produced a simple seek on the value 400, and it only does it once. Okay, you'd expect that, right? But let's do some geeky stuff. Let's stop it simplifying. And we're going to turn off a couple of things that simplification does. I'm going to talk about query rule off and things a little bit later on, but for the moment I just want you to know that I'm doing something that I shouldn't, and I'm turning off one of the abilities of the optimizers to do some things. So specifically, I'm not allowing it to normalize predicates, selection predicates. I'm not allowing it to collapse selections, which are restrictions, which are filters, remember? And I'm not allowing it to move a filter onto an index scan to turn it into a range seek. And I'm also using another trace flag 9130, which again the Dima from Russia introduced me to. It's very handy, which I will talk in more detail later on when we get truly sort of 400 level and Argenis wakes up. Oh, you're okay? Sweet. All right, so with that in place, the query plan we get is that. Okay? So we have a full scan of the product table. I'm going to hover over these. And then we get a filter that says product ID is 400. I get another filter, product ID is 400. So it's literally, I think that's great, yeah? Because it shows that internally, at some stage, it really was in that form, in the way that your query was written, or my query was written, or NHibernate's query was written. Okay, so there are 4 filters in a row. Completely useless plan. Completely useless, but evidence for the prosecution that that is exactly how it works. Alrighty. Simplification can also collapse domains. Again, we'll go into this a little bit more detail later on when we talk about domain properties. But here's a query that says product ID is between 310 and 41 times 10, which will be constant folded into 410. I can see you all busily trying to work out the ranges in your head. I've done it for you in the thing above. That collapses logically to the range 405 to 410 if you work it through. And if we look at the seek, indeed, it does collapse it into a single seek, 405. I'm getting confident with this now. 405 to 410. Okay, so that can be pretty useful, particularly if you've got dynamic seek or something. So you know the runtime parameters might have some sort of overlap or something else like that. Simplification is it's very cheap to do and simplifies the tree a great deal in some cases. And a simple tree is a faster tree to optimize, and also a simpler tree is has more chances for the optimizer to spend a bit of time thinking about alternative strategies. If it has to work with a hugely redundant tree to begin with, it's going to waste some time on exploring things that are just not going to be that productive. Okay, and equally, here's an OR. It used to be that people were scared of OR clauses, and they say, oh, they don't optimize well, and they didn't. I think back in SQL Server 7 or 2000, OR clauses were terrible. But the guys have done some great work over the years on index matching and things like that. So if I'm saying product ID between 110 and 210, or between 190 and 250, again, logically speaking, that is just a single range of 110 to 250, and indeed that's what it does. Okay, I think I've made that point, right? Now here's an interesting one, and I haven't really had time to dig into this yet. I only discovered it last night. You know, going through your slides for past that you've had prepared for months in advance, right? Yeah, so while I was writing the demo last night, I put I created a temporary table here. There's no rows in it, but there's a check constraint that says product ID must be between 1 and 100. And then I've got a query that runs on that table saying, give me the products between 50 and 150. Yeah? Now I expected simplification to look at that and say, yes, there's a check constraint. I can be clever about this. And indeed, it does. So it looks at the logic and says, I see, yeah. What you're actually saying is you want everything greater than or equal to 50. That's a quicker physical operation for me. I don't care about the 150 because there's already a check constraint. It's trusted, it's enabled, and all those good things. So I'll take that into account, and that's a nice little simplification. But originally I wrote this demo with a table variable. It's exactly the same, right? Unless I'm missing something. It's exactly the same. But the execution plan for this one says between 50 and 150. So for some reason that simplification doesn't seem to want to play with table variables, which I thought was interesting. Maybe I'll blog about it. What do you reckon? Okay, one more thing on simplification. I talked about computed column matching. So I've got a little table variable here with two integer columns and a third one that is column 1 multiplied by column 2. And there's a unique clustered index on that column. Notice it doesn't have to be persisted, by the way. You can create an index on a deterministic computed column without explicitly persisting it. If you persist it and then index it, I mean, I've done a clustered index, so it wouldn't matter, but if you persist it and then index it, you make 2 copies, right? But yeah, good to know. You don't have to. And then I'm doing a select where column 3 is 5. So seeking on that index on the computed column, and as you'd expect, we get a nice little clustered index seek, which is good. I write the same query with the expression, and because the expression is pushed down the tree towards the leaves, which is always good, the optimizer can match column 1 times column 2 equals 5, and simplify that to an index seek on column 3. Yeah? It's reasonably clever. And it does. So now we have 2 index seeks. I mean, so that's great. So you can go and create a computed column that matches a common expression in your real queries, create an index on it, and you don't have to do any work. You don't have to change your queries or anything. It'll just suddenly start using the index. That's really cool. But it's a bit sensitive to syntax. So if I now do the same thing where column 2 multiplied by column 1 is 5, so I've just reversed the column references, it's not an exact textual match anymore. Now we get a clustered index scan. That's annoying. A little limitation. Maybe they'll fix that one day. Something to be aware of. Oh, hi. Well, that's a good question. I don't know the answer to that. The question was, is it case sensitive as well? I don't know. Test it. Blog about it. I don't know. What, here? Oh, I suppose, yeah, I should, shouldn't I? You should be up here. All right, so if I change the second one... Oh, no, but I mean AdventureWorks, which is a case-sensitive... Oh, okay. I'm so glad you guys are here. So you happy with that? Yeah? Hey? Okay. Still get an index seek. That won't work for, the suggestion was to change that to a case insensitive collation, but that won't work for identifier column name matching. Ooh. Let's see. Will dividing by 1 work? No, that's too much for it. Hugo thinks that case won't matter because it's after parsing. Okay, Hugo. Let's try. Oh, you're right. Well done, Hugo. So there you go. It's my well-prepared demo shows. Case-sensitive. It's not case-sensitive. Thank you, Hugo. That's brilliant. Okay. All right. Now, another fun thing that simplification can do, again, this is one of Rob Farley's things he touches on, is if I do a join from transaction history to product, which has a foreign key relationship, which is trusted and enforced, but I don't actually reference any columns from the parent side, the simplification is smart enough to know that it doesn't actually have to touch the product table to satisfy this query, because there's guaranteed to be a product for every row in transaction history. So even though I've specified a join, the actual query plan is just touches transaction history and performs an aggregate. Okay? Again, very powerful. But not all projections are equal. And if you ever find something not being simplified in this way that you expect it to be, so you've got a foreign key relationship and you've written a query and you expect this simplification to occur, and it doesn't, all I've changed here is I've changed the product ID reference from the transaction history table to the product table. So I'm grouping by and projecting out p.product ID instead of th.product ID. Now they're guaranteed to be the same, right? Because that's the join predicate. So this should simplify, right? Erin's not so sure, and Erin is correct. It doesn't simplify out. Now for a long time I thought this was a bug, or a limitation, or an oversight, or something. And then a very smart guy called Remus Rusanu put me straight on it. It turns out that just because product ID and transaction, the product ID on the two tables compare equal in terms of the equality operator, doesn't mean they're identical. They could have different types. So one could be an integer, another one could be a tiny int, yeah? And there could be a cast going on, and they would compare equal, but I couldn't then just project out either one of them, whichever one I feel about. It could have different nullability, yeah, a different type. So if I was doing a select into a table, the column that got created would have a different type if it did that sort of thing. So, yeah. I often encourage people to be really careful about types and things like that. And that's just one example where following the exact rules of what you mean is important. Otherwise, that simplification doesn't actually apply. All right, I thought that was interesting. I talked earlier about simplifying outer join to join, and this is a simple case. You see it on the forums all the time. Someone's written an outer join like this and then a where clause that rejects nulls on the preserved side of the join. And as you'd expect, that's logically a join, so it doesn't bother to do a left join followed by a filter. It just does zoom, an inner join. Okay? So quite often if you write a query and you write full join, right join, left join, whatever, and you see an inner join in the result, it either means there's something wrong with your query and you're accidentally rejecting the nulls that might be preserved in some case. It's always a good indication to me when I'm tuning a query. If I see an inner join where I expected something else, I have to go back and check my query. But it's clever enough to go further than that. Okay? I mean, that's amazing enough, right? But because it's based on relational algebra and the theory of sets and things like that, modified for SQL's weird semantics, if I take the same query and put a distinct on it, yeah? So you'd think, well, it's a left join, then a filter, then there'll be a group by. So it simplifies the left join to an inner join. And then because I'm doing a distinct, what I'm logically doing here is a semi-join. I'm doing an existence test. And the optimizer is clever enough to recognize that. And we get a left semi-join, which can be a lot more efficient than performing a full inner join, right? Does that make sense to everyone? Adding that distinct would have that effect. Logically, it has that effect, and the optimizer thinks in terms of logic. Yeah. But it has its limits. So if I do the same thing, but I say where product ID is null, and again, this is a pattern I see all the time on the forums. They say, I want to find things in this other table that don't match, so I'll do a left join and then check for nulls. Seems crazy to me. You'd write that as a not exist, right, or an except or something. But some people find it very logical to perform a left or a right join and then find the ones that came back with a null in them. Mm. Okay, so the comment from the audience member here in a very fetching stripy shirt is that in earlier versions of SQL Server, that syntax could perform better. And that's a fair point. But generally speaking, I encourage people to write queries logically to begin with. And then if you don't get acceptable performance, then try syntax tricks. I certainly wouldn't start by writing a left join and then rejecting nulls. Okay, I would start with not exists or except. It's more of a logical specification than worrying about the physical stuff. And it's not true anymore anyway. All right, but it has limitations. So if I write the same thing with a distinct and saying it is null, I might hope for an anti-semi-join in the query plan, but I don't get it. I get a left-outer join followed by a filter. Okay, it's just a transformation that they haven't implemented yet, and they probably never will. If they haven't done it yet, they probably never will. It's something to be aware of. So yeah, I would write it using an except in this form, in which case we do get an anti-semi-join, or perhaps using a not exists. The except form is arguably more compact, but you get the same query plan.
Can you execute all the 3 together?
Question is, can I show all 3 together? I will try. Screen's not very big though. Oh, I can get 2. Okay, so the top one is left join filter, then those 2 with except and not exists are the same in this case. They wouldn't always be the same. Because, that's not me, is it? Wow. What a noob. Fantastic. I hope that was someone important. I'm giving them grief later. All right. And we can also specify an anti-semi-join using not in. I mean, you have to be careful with this one because it all goes horribly wrong if the thing inside the not in produces a null, you get no rows. I mean, everyone knows that, right? But you can. In this case, it's semantically the same. And we get the same query plan. So syntax independence is a big thing, right? The optimizer does work pretty hard to mean that you can specify your query in the way that you find most natural to you. Yeah, I have a particular way of thinking about queries and writing things, and if the optimizer were perfect and considered every possible rewrite and transformation and simplification, your queries would run very slowly, but you could write any syntax that was logically the same and you would get the same execution plan, right? It's not quite that good, but the general advice I give people is to write using natural syntax that makes it look simple and understandable and maintainable to you, and then tune for performance later on by changing syntax if you have to. All right, now here's that one I showed you before, big complex full outer join CTE type thing. If I do a select star from that, we get this, let's zoom to fit, big query plan, lots of full joins and things. But if I just project out a few things, just referencing one table, simplification is smart enough, it can reason about all these foreign keys and things, and pull it down to that simple index seek, which I think is a beautiful thing and well worth seeing twice, I think. Well worth seeing twice. Okay. That's simplification. All right. Okay, big section. By the way, I appreciate that the first half hour isn't that exciting, but I have to do the groundwork for the early stages of optimization. All the cool stuff is yet to come, so please, if you need a nap, that's fine, I don't mind, but it does get quicker later on. So cardinality estimation. Cannot overstress how important cardinality estimation is. So cardinality estimation is just the number of expected rows at each point in the logical tree or physical execution plan. SQL Server's Query Optimizer is a cost-based product, as they all are these days. So it makes decisions based upon its anticipated cost of various alternatives. Now, all that is predicated, if you will, on cardinality estimates. If cardinality estimates are good and the model is, pretty good, then you'll get a great execution plan. if the cardinality estimation is wrong for whatever reason, then all the clever code inside the optimizer that reasons about alternatives and says, oh, that's more expensive than that one, I'll do this one, is going to be wrong, right? So this is the absolute fundamental to making good use of a cost-based optimizer, is to have good cardinality estimates. Okay. So where do these cardinality estimates come from? Well, they come from the base table cardinality itself. SQL Server tracks the rough number of total rows in each table on the system. It keeps, as you know, density or frequency statistics and a histogram in the statistics that you create and the statistics that I hate that word, the system creates automatically for you. So by default, you have auto stats and auto update stats turned on, right? Yeah? Is it because it's Friday, or are you so jaded from your sessions you make a noise or something? They're alive! Okay. Yeah, so we have these base table statistics, and we also have something called tri-trees. Well, I pronounce it tri-trees. And there's some good academic papers around if you search for them on Bing. I'm told I ought to say Bing. It's a very, very clever piece of academic work. Matching a string to percent something percent, if it's a short string, it can use tri-trees to pretty accurately guess the cardinality estimate on that. And that blows my mind, because you'd think that would be completely non-sargable, you couldn't reason about it at all and say, there's an E somewhere in the string. Yeah? But this thing called tri-trees, I haven't got time to go into it and I don't fully understand it, so I can't describe it to you, but clever, yeah? Like really properly clever, academically clever. Not well known is the fact that in a query plan, so it's got full statistics and things at the leaves of the plan, so a full scan of the product table, it knows the statistical distribution, it knows the number of rows in the table, but then you might apply a filter or something, or you might perform a join. And what a lot of people don't know is that the optimizer produces derived statistics. Each time it does a compilation, it takes that histogram and applies math, science, and logic to it to derive a new histogram. Yeah? So the 200-step thing you see in DBCC show statistics, it derives a new histogram for each step of the logical tree. So it knows about things like filters, yeah? And it can say, what effect will this filter have on the statistics? And it produces a new statistics for the next operator to work on. And this is how the cardinality estimate thing works. It says, I've got 1,000 rows in my table, I've got a filter that has like 25% selectivity, so after that I expect, oh my goodness, what did I say? 25 rows, let's say. Yeah, that'll do. 25 rows, but they'll have this distribution. So it has if you use relational, simple language, and it translates into a simple relational execution plan, they've done all the work to do all the math and science to work out what effect that filter will have on the histogram and produce a new one. So the next thing has good information to work with. I think that's awesome. And so the cardinality of tables and things like that is also taken into account in choosing an initial join order. So you've got 4 or 7 or 12 tables in your query all joined together. It cannot physically explore all the possible 12 factorial combinations of joins. So it has to choose a reasonable starting point. And there are all sorts of heuristics based on, we do inner joins before outer joins. We do things that have high selectivity and reduce row counts first and things like that. It generally works pretty well. But yeah, so it does start with an initial join order. But all this science and math and stuff does have to make some assumptions, okay? And this is where it starts to come unraveled sometimes. But you have to make assumptions to keep things reasonably workable and to make them perform reasonably well. So one of those is the uniformity assumption. So if SQL Server doesn't have statistics about the distribution of value, it'll assume that it's uniform. Okay? Sounds simple, but it has big implications in a lot of queries. If it doesn't know, it will assume that it's uniformly spread over the range. Independency assumption, it assumes that, so you have 2 clauses where something equals something and something equals something. It assumes that the selectivities of those 2 things are completely independent. The classic example where that breaks down is you have a table of cars and you have where manufacturer equals Toyota and model equals Prius, or Prius? Prius? It assumes that those two predicates are completely independent. So if the first one's 10% selective and the second one's also 10% selective, it'll multiply those together and assume that the combination of the two is 1% selective. Whereas, of course, all Priuses are Toyotas, right? So there's a correlation there, which is where multi-column stats and filtered stats and things like that can come in useful. But it's an assumption that it makes. It's changed a little bit for 2012, I think, but anyway. There's an inclusion assumption. If you compare something with a constant, then you're going to find a match. This is one of a general class of assumptions that means if you go looking for something in your query, the assumption is that it's because it's there. Yeah? You do a join on a where something equals something, the assumption is that there is going to be a match. Right? And the base containment assumption, I do not know how to explain this. If you're joining two things together and the number of distinct things in this range is smaller than the number of distinct things in this range, it assumes that there will be a match on every single one of them. It's a bit scientific and stuff. But it only applies to base tables, not the derived statistics I was talking about. There are a number of options that you can enable to change the behavior of cardinality estimation. Traceflag 2301 is one that still works. Decisions support extensions. It can make your optimization time increase, but it does apply more sort of logic and heuristics. Sometimes it will give you a better cardinality estimate where the sort of basic reasoning isn't enough. I've never found it tremendously useful, but I guess in some workloads it could be. There are some improvements in SQL Server 2012. The correlation thing, the no correlation thing seems to have been relaxed a little bit, but I haven't fully worked out what that is yet. And the other thing, does there anybody, you know the connect.microsoft.com site for reporting bugs and making suggestions on the product? Does everyone use that, yeah? So that's a great place to look because the developers leave comments and things all the time and sometimes they say things that they probably shouldn't. Yeah, it's awesome. So I have so much free time, I just scan through Connect looking for things that Andrew Richardson has said recently. Although, to be fair, they have also said it on MSDN forums. There's been a couple of comments saying that they are doing extensive work in the area of cardinality estimation and things like that at the moment. So I fully expect to see maybe, I don't know, larger, more histogram steps, better logic in certain areas, something like that pretty soon in the product, which is quite exciting. Because so this 200-step limitation has always been an irritant, especially on large tables. But I guess if you're deriving new statistics at each step of the plan, you want to keep that number small so your compilation time doesn't go crazy, right? All right. Now, as I mentioned, it uses a complex mathematical model and heuristics, and only a subset of the possible operators are included in that model. And if it's not in the model, then you'll get a guess. And guesses are more likely than not going to be wrong. When I say math and logic, I'm talking about stuff like this. Okay, this is actually some of the logic from a research paper that came out once about how to find selectivities on a predicate. And there's more stuff like that, and stuff like that, which is all very entertaining. And there's that one as well. That's good. If you're wondering how to align the histogram steps when they were misaligned, this is how they do linear interpolation to do that. And there's that one as well. Okay, so that's all you need to know. All right. Cardinality estimation, available for download, just work it through, it'll all be fine. Sweet. So things that are covered by the model are the things that have been around for a long time, that are pretty simple and that are relational in nature. So a filter, that's a pretty simple thing, you have to be able to filter, right? But a relational select or restrict, do a good job of modeling that works well with the model. Inner join, semi-join, anti-semi join, outer join, basic relational stuff. If you write relational queries, you write them relatively simply, chances are your cardinality estimates will be pretty good. If you don't do that, you use funky new stuff, you combine it in lots of ways, you use complex expressions, you nest it inside a substring left, whatever, it won't even bother trying, it'll just guess, and you'll get a plan based on a guess, which is no better than not doing. Why would you cost-based optimize based on a guess? It just makes no sense, right? So I can't really overstress this. If your cardinality estimates are wrong, you're getting a rubbish plan. And you can't really blame the optimizer for it. It had no good information to work with, right? All right, sound reasonable? All right. So I have a quick demo on cardinality. It's actually showing a little bug. Because just showing you cardinality estimation would be pretty dull. Yeah, look, estimated number of rows. There you are. That's all it does. All right, so preamble and connect. So I have a query here. Looks at the transaction history table for product number 1 for a particular range of dates. And we have this estimated plan here. So it's doing a seek for product ID 1. It's estimating 45 rows. And then it's doing a lookup on the clustered index to find the other columns I needed from my query. And it's estimating, it's estimating 16.9951 rows. Well, that's ridiculous. Hang on a minute. It's doing a seek, and then a lookup per row, but it's a lookup into the clustered index based on a row from an index that's guaranteed to be 1 each time. Can't be anything else. Okay? By definition. So where's it getting this 16.9951 from? And the final result is 45. So I'm taking 45 rows, iterating and producing 16.9951 each time, and that's resulting in 45 rows. Yeah? Now, math was not my strong point at school, but that can't be right. That can't be right. So I'm going to use that 9130 trace flag that I mentioned earlier. And what this one does is it pushes a non-sargable predicate into a scan. What it does is there would normally be a filter operator saying where transaction date between 1st of September and 31st December on top of a seek or a scan. And what this optimization does is to move that filter into the scanning or seeking operation. Yeah? It's an important physical optimization because it means, because all these things happen a row at a time, otherwise it would be get a row from the scan, pass it over to the filter would check it. If it didn't pass the filter, it would go back to the scan, get another row. So there's lots of latching on memory pages and things as it does this over and over again. By pushing the predicate into the storage engine, as it does the seek or the scan, it can get the row, check it, get the row, check it, get the row, check it, and pass it on. Okay? So, but I'm going to turn that off with 9130. Again, undocumented, unsupported, don't use it except for entertainment. But if we do that, we can see the filter that had previously been pushed down the plan into the index seek, into the key lookup, is now in an explicit filter. And the estimated number of rows out of that filter is 16.9951. Okay, so what happened before is it pushed this filter down the plan into the key lookup and copied this cardinality estimate of 16.9951 on top of this correct estimate of 1. Yeah? A lookup is always 1 row per iteration. So what it's done is it's pushed the filter down, but it's messed up the cardinality estimation. The 16.9951 should be the result of all the lookups, not each lookup. Little bug. Which, thanks to the amazingly receptive guys at SQL Sentry, Go SQL Sentry, has been fixed in Plan Explorer just a couple of weeks ago. I worked with them on that. So if you use Plan Explorer, raise a hand. Good on you. Good effort. Those people who don't, download Plan Explorer. It's free, and generally speaking, pretty awesome. I still use plans in execution in Management Studio for the sort of detailed analysis I do sometimes, but it's got some very cool things. So I'm going to try and view that with Plan Explorer to show you that it is fixed. Yes. So let me try and zoom that for you. So Plan Explorer, of course it does. Muppet. Bear with me, kids. I'm getting there. So the original plan without the fixing it trace flag. Okay, so 16.9951 is wrong. View it with Plan Explorer. Plan Explorer knows that this bug exists and does some clever math to work around it. So we see 45 rows from the seek, a grand total, because Plan Explorer does totals on the inside of a nested loop joint, is 17 rows, producing 17 rows on the output, and that makes logical sense. Okay? So if you've got a predicate that's been pushed into a key lookup, so if you hover over a key lookup or an RID lookup, and there's a predicate on it, the estimates may well be wrong because of this bug. Happily, it doesn't affect the optimizer's plan selection. It's just something, it's a display issue. But I just wanted to mention it because I wanted to do a demo on cardinality estimation, and anything else would have been really, really dull. All right. We're breaking at 2:30, right? For 15 minutes? So let's do another 15 minutes. All right. So the next thing after cardinality estimation is, if it can, it'll try and find a trivial plan for the query. So this is for queries with no real cost-based choices. But the key to it is the optimizer has to be able to quickly recognize that there are no cost-based choices. There can be queries with no real cost-based decisions to make, but it's too hard for the optimizer to see that, so you'll still end up going through full optimization. I love the way people duck on the way out. I'm not here. Can't see me, right? It's a fast path through optimization to avoid the costs of full optimization. Full optimization is awesome, but it's got all sorts of setup costs and things. Are you laughing at me, Erin? You are, aren't you? It's got all sorts of setup costs. It's an expensive thing to get into. So if we can find a trivial plan that is obviously going to be correct, then we'll try and do it now. The details of what things qualify for trivial plan and which things don't changes between versions. I can't keep up with it, but generally speaking, if it's a very simple plan, you should see a trivial plan. But if you have a subquery or a join or an inequality predicate, some query hints in older versions, that restriction's now gone away. Or if your cost threshold for parallelism is low, that's an interesting one, which I'll demonstrate in a second, then you will never get a trivial plan. Okay? All these things will produce, because there's going to be a cost-based choice. If there's a join in your query, it's at least got a choice between a nested loops join, a hash merge join, or a merge join. It's got to make some sort of cost-based decision at some stage. So it can't just choose an obvious plan and go with that. But if it does find a trivial plan, then that's it. That's the end of the talk. Thank you for coming. Optimization ends here, and the query goes off, gets cached, and executed. Okay, so let's have a look at some trivial plans then. Does everyone know what I mean by a trivial plan, by the way? In Management Studio? No? Okay. All right, trivial plan. Trace flag on. So here's an example of a query that will produce a trivial plan. Find me the products from product ID where the name is Blade. There happens to be a unique index on the name column, so there is an obviously best plan for this query. Yeah? We're just going to seek that index. It's obvious. There's no real magic to that. There's the plan. And if you click on the root icon, the select in this case, and bring up the properties window with F4, F4 should be the key you use most, unless you use Plan Explorer, in which case it's different. So bring up the properties of that node, and we'll see. Let's do the zoom thing. There we go. I'm determined to get this right. Live zoom. There. Happy with that? So the optimization level is trivial. So this plan is a trivial plan. And somebody today was doing an awesome session on mining the plan cache for this sort of thing. So there are queries you can use with who was it? Jason Strait, that's right. So you should have gone to that. If you have a time machine, go for it. Yeah. I've got to stop coughing into my microphone. All right, so that's an obvious trivial plan. But I can do something a little bit more complicated. I can introduce a windowing function into this query. I put a row number over order by name. And got a slightly more complex plan. It's got a segment iterator to break things into groups and set a little flag to say when a new group's coming along. It's got a sequence project. to add the row number, but this, I'm not going to draw a blue box this time, but I'll zoom for you. There you go. Trivial plan. Okay, so still a trivial plan. No cost-based choices to make. There's an obvious plan to it. Alrighty. But a subquery prevents a trivial plan. Same query, and all I've done is wrap the product ID in select. It's obviously exactly the same, right? But this time, yeah, full. So it hasn't found a trivial plan, it's gone all the way through full optimization, just because I put that little subquery in there. Okay?
Can you run both together? See the cost?
The question is, can I run both together? No. So you want that one and the first one, yes? Okay. No worries. You're going to ask me why there's an extra compute scalar there, aren't you? Yeah? Hmm?
Same relative performance.
Okay. Yes, same relative performance. Oh, you're looking at the batch percentage cost. Oh, please don't do that. Okay. Soapbox. Estimated costs, yeah, in execution plans. Okay. It uses a model internally to cost these things so it can choose between alternatives for the same query. It might use a merge join, a hash join, something else. And it looks at all the alternatives and says, right, that one's cheaper. That's what it's for. If it's the same query, then yes, in this case, it's a valid thing to do because they're a similar plan for the same query. But it drives me nuts when people run a script and then compare the batch percentages. What you're comparing there is the optimizer's estimate of the time it's going to take to run. But for all sorts of hideous internal reasons, they're not guaranteed to be comparable between one plan and another. It's just a number that's used for comparing alternatives for the same query. All right? Yes, you will find some correlation sometimes that one query will be 60% of the batch and the other one will be 40 and whatever. But that is purely, well, it's mostly coincidence. Please, please, please do not rely on comparing these batch percentages. Do performance tests. Check logical IOs, CPU usage. Use DM exec query stats or something. But yeah, don't do that. Yeah, CPU cost, memory usage, buffers through the buffer pool, whatever you want to compare, all good performance metrics, excellent. Just don't. I wish they'd take these percentage relative to batch costs out of Management Studio. It's not helpful, and it leads people who are new to the thing to do a comparison which isn't valid. Okay. Another quick example here, just showing that inequality prevents a trivial plan. So this one is also full optimization. And there's always a trace flag. There's always a trace flag. In this case, it's 8757. Again, undocumented, but what it does is skip trivial plan. So if we do that with 8757, we won't get a trivial plan because the magic trace flag says not to do it. There you go. Full optimization. It's always a trace flag. And the final thing, just to take us up to the half-past break, I mentioned that setting the cost threshold too low. So if I set my cost threshold for parallelism temporarily to 0, because I'm insane, well, I am, then our original simple query, same query plan, look at that. Full optimization. Now, why has it done that? Well, because the cost threshold for parallelism is 0, whatever estimated cost this thing comes out at is greater than 0. So it says, think about a parallel plan. But that's a cost-based choice straight away. The choice between a serial plan and a parallel plan is a cost-based decision. So it cannot choose a trivial plan. So you will never get a trivial plan for a query that has an estimated cost greater than your estimated cost, your threshold for parallelism. All right? Cool. Did I explain that okay? Yeah? Okay. I'm just going to reset that to where we were. I don't recommend 5 as a default, by the way, just resetting it back to what it is with my vanilla install. Now, just a quick word about auto-parameterization, because this is SQL Server goes a bit further than trivial plan. If it recognizes that it can produce a trivial plan, it'll also try to parameterize it for you anyway, as if you'd done the right thing yourself and put a parameter in there. It'll try and sort that out for you. So let me create a quick non-clustered index on the person table, which is going to help the query I'm about to run. Clear my plan cache out. And then show you a simple query that's looking for addresses in Seattle. See, context-sensitive demos. Awesome. So these are the addresses here, and it's estimating 141 rows. Now that's a trivial plan. Yep, trivial. And it's also been auto-parameterized. Now I'm not going to show you that it's been auto-parameterized because there's no reliable way to see that from MS that I can work out. Sure, you get a parameter list and whatever, but that just means that auto-parameterization was attempted, not that it necessarily succeeded. But if I run the same query with London instead of Seattle, obviously you get different results. But the estimated rows there is still 141. This is a parameter sniffing thing, okay? So the previous query with Seattle has been parameterized and cached, and now it's been reused for a query that specified London, even though we did no explicit parameterization like we always should. And I can show you, via the magic F4 button, the parameter list there. So we have one parameter, labeled @1, and the plan was compiled with a value of Seattle and executed with a value of London. Okay, so this is auto-parameterization for you. Are we having fun yet? Oh, yeah. And then we have Pigeon Forge, which only has one address. I want to live in Pigeon Forge. It's a great name. There's only one person. Yeah, so actual number of rows 1, estimated number of rows 141. Parameter sniffing. Not necessarily a bad thing. Yeah, if most of my queries were in that sort of general area, that would be a great optimization. It just happens not to be exactly right in this case. I don't care, that's fine. But again, our friend F4 will show us Seattle and Pigeon Forge. I'm getting casual with the zoom now. And it's still a trivial plan. Yes, sir. Klaus. Does it matter that we have the... No. Yeah. So the question was, does it matter that I have a parameter sniffing problem with this query? And it isn't a problem. That's a perfectly fine plan. For any of those parameters, it's a perfectly good plan. The estimates just don't happen to be the same. We should relax about that, yeah. Parameter sniffing can be an issue, but... So I mentioned it's not really possible reliably to see if a plan's been auto-parameterized just by checking the F4 properties or something. Sorry, yes, another question.
Why is it we prefer a trivial plan over a full plan?
What? Question, so why do we prefer a trivial plan over a full plan? Simply because it's very much quicker to compile. So if a query's been run a lot or recompiled a lot, it's much better, much faster for it to be a trivial plan. Going into cost-based optimization has all sorts of startup costs and memory usage and CPU effort and stuff that if you've got a very small trivial query, you don't want to spend 5 milliseconds compiling it if it only runs for 1 millisecond. Yeah? So trivial plan is a good optimization for simple queries that need to run a lot and possibly recompile a lot. So I've got a horrible query here that Jason Straight would be very, very proud of me for writing. It's interrogating the plan cache, looking for a parameterized plan handle value and a parameterized text thing. So in that case, I have my 3 queries for Seattle, London, and Pigeon Forge, or whatever it was. There's an entry in the cache, just a stub, for the literal form of the query, which is those three at the top. And then the line at the bottom here is the auto-parameterized plan. You can see with the at1 in varchar 400. And you can see it's been used 3 times. Ooh, scrolly scroll. It's been used 3 times, and it's listed as a prepared compiled plan, not an ad hoc compiled plan. So this is auto-parameterization and a parameterized plan being reused. This is the desirable state of affairs. But it really should be easier to drill into this than writing XML like that. Okay, it's past. Oh, Erland. Erland has a question.
Go back and run one of these squares with the London
Oh,
arm.
you found a flaw in my logic, haven't you? You want me to run the London query again? Yes. Yep. Execution plan? I beg your pardon? Yes, there is. But what I'm saying is that just means that parameterization was attempted. There's a performance counter for safe autoparam and failed autoparam and things like that. So it'll attempt auto-parameterization a lot. But if the optimizer detects that it wouldn't be safe to parameterize the query, you still get the at1 in the query text. I haven't found it to be reliable, anyway, is my point. Okay? And likewise, in the F4 window, the parameter list can sometimes be populated for a plan that hasn't actually resulted in a prepared plan going into cache that can be reused. I need to summarize that for the recording. I need to show a demo where it proves my point. Thank you, Erland. I feel like a failure. Thanks, man. Okay, so that's just gone 2:30. We'll take a 15-minute break now, and when we come back, we'll get into cost optimization and stuff. Thank you. It's just great to see people in person with names that I've looked up to for a long time. Okay, I was going to do another demo on autoparam, but if I get time at the end, I might come back to it because I've got a lot of stuff to cover on full cost-based optimization. So if you're all ready, I'll get straight back into it. All right, so that was the trivial plan demo. Now, if we can't find a trivial plan, which will be the majority of the time, right? We need to get into the fun stuff, which is cost-based optimization. So we start with the logical tree that's come through simplification and all the previous stages. So you remember the logical tree familiar, the pretty thing with all the nice pass-mandated colors. Now we want to look to explore logical alternatives that produce the same results for every possible case. So remember, it's not just the specific query you've written that gets cached. It could get reused in the future. So when we're looking to be clever to find an alternative physical execution plan, we need to find one that is correct for all possible parameter values, all possible states. So that's a little bit of a restriction. Okay. So the general process is to generate a physical implementation for each logical alternative that we can find. Estimate the physical cost of each physical... My microphone's in the wrong place, isn't it? A cost for each alternative physical implementation that does the same logical thing, and then choose the cheapest one, which I've labeled as easy. So the process as a whole is pretty easy, right? You take a query tree, a logical query tree, find one that's logically equivalent in all cases, do a physical implementation of one sort or another, cost them up, and then choose the cheapest one. Simple as. We'll be out early. Now, the SQL Server Query Optimizer uses a framework called Cascades, and it's something you can look at. You can Bing Google it. It was, politically dodgy ground here. If the door opens in the stage and I disappear, it's Yeah, it's based on a thing called Cascade Framework. So this whole idea of exploring equivalent logical trees for various things isn't just limited to query optimization as a problem. There are all sorts of general problems out there that can benefit from a framework that makes it easy to search for things that are logically equivalent and to cost them up and find the cheapest one. Cascades was an academic work that evolved from previous efforts that was called Volcano, you could look that up as well, and Exodus and Starburst and other optimization frameworks like that. But Cascades was particularly good. It's written by a guy whose name I have no hope of pronouncing correctly, but I'm told he was German, and I'm going to say it was Goetz Graefe. Okay? It's spelt G-O-E-T-Z. I'm going to pronounce that Goetz. And G-R-A-E-F-E, Graefe. What do you reckon, Ben? Close enough? Close enough. Massively clever guy. He worked for Microsoft for a while, so he wrote this thing. They brought him in, they bought Cascades, and they implemented it in SQL Server 7, I think. Okay? But that's the name of the general framework. Okay? It's extensible and modular. That's the point to it. What you don't want to do is what some other popular database, Oracle, vendor did, and write a rule-based optimizer so that every time you introduce a new feature or something, you have to write a whole bunch of new rules specific to that feature and hope that it works well with everything else. Cascades works across query boundaries, so you've got subqueries. There are some optimizers that wouldn't look inside the subquery to look for optimization opportunities. But it's very general, it's a top-down optimizer, and very easy to extend with new operators. So when the row number and rank and things like that came along, they needed new physical and logical operators in the module to reason about the costs for alternatives to those sort of things. You just implement the basic interfaces that are common to the Cascades framework and slip it in. I'm sure there's a bit more to it than that, but in principle it's very extensible and modular, okay? Very nice piece of work. There's a number of academic papers out there, if you enjoy reading that sort of thing, by this Goetz Graefe person, that go into all sorts of hectic detail about sort algorithms and optimizing spills to disk, and he's written on a lot of stuff over the years. It's deeply, deeply interesting. Helen?
Sorry to interrupt. We've lost the feed to the capture box, so if you get a chance, could you just refresh your resolution? You don't have to stop.
Refresh the resolution.
Yeah, you just go to just change it to 1024 by 768 one more time, please.
Oh, bro, I don't know.
Something changed in the
Okay, they've lost the feed to the thing. So you want me to just change that to itself? Or change?
Or just hit detect one more time and see if that makes a difference. Top right corner.
Sorry about this. Technical difficulties. Detect.
Yes, please. And that's the best we can do without stopping it altogether.
Okay. Oh, that's a shame. All right. So, technical difficulties aside, you're lucky you're here. Otherwise, you might not be able to watch this. So the optimizer's goals, then, are not to find the perfect plan. I've seen all sorts of texts over the years, and I know why people wrote this, but they said, yeah, the optimizer finds the ideal plan. But it doesn't. It has no such goal. That would be ridiculous. You've got a complex query, ICA string, and the digits themselves, if you separate it into 2 bits, 2 digits per character, and do an nchar on it, we'll find something interesting. I'll do that now for you now. So I've taken that number and split it into 2 bits, ncharred each one. If we run that, it's A to G. So that's how that works. In the query tree, they actually just convert it to Unicode, and the thing works on it. Klaus! Oh, for the benefit of the recording, Klaus is mean. Klaus Aschenbrenner thinks I have too much time on my hands, and I probably do. Hey, I have friends. I have a friend. Adam tweets me. All right, so that's the end of that demo. It's just a little thing for you there. All right. Okay. Now, I'm trying to approach this in a sort of logical fashion. It gets disjointed in places because I have to start referring to things that I haven't defined yet. So I apologize for that a little bit, but I need to do a little bit more groundwork at this point. So talking about this logical tree, as I keep doing, in order for the optimizer to reason about things, it sets lots of things called properties on each node of that tree. Okay, so I showed you some of them. There was a cardinality estimate and the A to G thing. But there are other things that are logical and physical properties associated with each node. Examples of logical properties are the input and output columns that are associated with that particular node. Okay, so it's product ID going in and product ID coming out. The types and whether they're nullable or not. Which columns are key at that point. The functional dependency, so the columns that depend on the key. All this information is useful for it can reason about things that it can either skip doing or optimize away or take advantage of foreign key constraints, something like that. So logical properties tell it things about your data that allow it to make optimization choices. And also the domain ranges. So the thing we saw earlier where the overlapping ranges got compressed down to a thing. As the tree flows upwards, it keeps track of the possible range of values all the way it goes along. So sometimes you'll see an interesting simplification in your query plan that you weren't expecting. And you just have to compare back to the metadata in your database about the check constraints and things like that, and you can generally work out how it's managed to work out that a thing cannot possibly be null at this point in the plan, or it must be greater than 10 or something like that, and it can take action in that way. Okay. Domain property framework, I think Connor calls it. There are also physical properties as well. There are actually hundreds of these, so Connor tells me. I don't know what they are because they don't expose them, but you can sort of guess. Physical properties include things like a sort order. So at a particular node in the tree, you might be coming out of an index seek. So you'll be getting rows ordered by whatever the key on that index is. I should probably mention at this point that the execution plans I've been showing you so far, they're not execution plans. They're not pictures of execution plans either. They are pictures of an abstraction of an execution plan. Because what we see is not the thing that gets executed. It's a lot more complex. And there's a lot more guarantees and code going on. And the reason I mention it is not to make you feel inadequate or anything. There's a load of good information there. I'm just saying don't take it too literally. Don't infer things that you shouldn't. So if you see rows coming out of an index seek and it says ordered true, and you see the next operator, we can't assume that it's guaranteed that those rows will come out in order. It's the old thing about not using order by on the end of the thing and relying on it. Yeah? The same thing applies intra-operator within the query tree. You can imply things by looking at the properties, but don't get too carried away because what we're looking at is what they choose to expose to us to help us understand the performance implications of the choices in our query plan. Okay? So I'm just saying don't take it too far. Unless you've got the source code. In which case, my email address was up earlier. All right. Sorry, what? Oh, Halloween protection, I'm sorry. Oh, yes, there's a load of physical properties, not just sort order and me going off on a rant. Yeah. So information about partitioning and cardinality-derived statistics. Halloween protection. Okay. Halloween protection is the generic name for what was originally an update problem. And this is where it gets confusing because the query processor people, everything is an update. Anything that changes data is an update. So an insert is an update is an update, a delete is an update, and a merge is an update. It's known as an update internally. And Halloween protection is something that occurs when you're reading from a table that you're also, or an index or some access method that you're also updating. But because it's two cursors, a read cursor and a write cursor, you're doing it row by row. If you make changes here, it could be ahead of the scan where you're reading from, so you can encounter the same row again. The classic example is where IBM or whoever it were, they were running an update program to increase everyone's salary by 10%. So update salary, set salary equals salary times 1.1. And the query never ended because it would update a row, give you 10%. Oh, and then it'd find it again, ahead in the... I mean, it would have crashed eventually. But it's not just update queries that need Halloween protection. The most basic form of Halloween protection is phase separation. So you'll see an eager spool or something in the plan. So the read cursor part executes to completion. All the rows go in the eager spool, stored in tempdb, and only then does the update portion of the plan start executing. Okay? Phase separation. Separate two things, they can't interfere, life is good. Unfortunately, spooling everything into a table in tempdb is not always a performance win. So there are other alternatives. And again, the math and science involved here is fantastic. So there are different operators, different physical operators in the query plan, because of their physical nature, happen to provide a certain level of Halloween protection if you really dig into it and think about it late at night with coffee. So a sort operator, because it has to consume all its input before it can start producing output, provides phase separation, so you don't need an explicit table spool. So they have a whole framework for reasoning about Halloween protection. And by the way, it's not just update plans that, whatever, inserts, self-joins are a particular problem. You do a hierarchical self-join on an insert or a delete. There were some bugs in SQL Server 7 and 2000. You can search for them on the support site. They were real bugs that bit people, and values would either get updated or you'd get a retail assertion or bad stuff. So yeah, Halloween protection is there to ensure that updates in the most general sense perform correctly. Have I done okay on that? Yes, another question.
Does the optimizer know about read-only file group? Or that wouldn't be an issue, it would have to go to the eager spool because it can't be updated?
So the question was, does the optimizer know about read-only file groups, and that wouldn't be an option? Well, it's tricky to know what an update plan would do on a read-only file group. How would you run an update query on a...
Well, I think that if you were selecting, or is it only when it's the same?
Oh, it's generally when it's the same structure, yeah. 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 Yeah, sorry. But no, to answer the general question, I believe not. In terms, the optimizer is generally agnostic to things like locking and transactions and read-only file groups. That's all storage engine stuff. Yeah. Stuff from the storage engine has leaked into the query processor mainly for performance reasons over the years, so that the separation isn't what it was. But no, in general, it doesn't really reason too much about that sort of thing. Okay, rules. So I've talked about properties. So each node in the logical query tree has all these properties associated with it that help the optimizer make its decisions. And the rules are the things that are the engine of the optimizer. It has, well, SQL Server 2012 has 397 rules, and there are four sorts, four broad categories. Simplification rules, which we met earlier when we were doing all the simplification demos. Again, they're all or nothing, they're always good, and they're a linear application. So it doesn't store alternatives, it just applies these rules if it can, because they're always good, and you end up with a simplified results. And those are simplification rules. Exploration rules are the most interesting ones. These are the ones that take the query tree or a part of the query tree, match a particular pattern, find an alternative, and generate a new alternative. Okay? We'll go into detail on this in a moment. Oh yeah, 397. I remembered that correctly. But the thing about exploration rules is that they do keep the alternatives hanging around. So simplification was all or nothing and a linear application. If I start with a plan and I find a little bit of it that I can explore and find a new alternative, I now have 2 alternatives. And then I could find 3 and 4 and 5 and 8 and 12. So there can be a sort of combinatorial... You can get a lot of alternatives very quickly. You should have heard me in my parallelism talk the other day. Parallel execution. There are implementation rules. So when you found a new logical query tree that's semantically identical to the original one, we need physical implementation rules to find physical operators for those logical operations. So we can have a logical join, and our physical alternatives could be nested loops, merge, or hash, or some other funky type that they could choose to introduce in the future. Who knows? And the final one is a little technical one called enforcement rules. So things like merge join and stream aggregate and sequence project, things like that, require a sorted stream. So there are properties and rules that enforce a particular sort order at a particular point in the plan. Okay, there's no point exploring different alternatives if they don't provide the correct sorting So you have a sort enforcer on the input to a merge join, so that whatever alternative is generated, whatever alternatives are generated, must provide the sort order that's enforced by that enforcer. And Halloween protection is an enforcement thing as well. Okay, so those are rules. These are the things that we're going to focus on the exploration ones pretty much. So I talked about pattern matching, a part of the logical tree. So a rule will have associated with it a pattern that it would like to match to in the query tree. And if it does match, we have here a select, a filter, a relational select on top of a join operation. And there's a simple rule called sel on join, which is select on join, which would just provide a new alternative, which is those two things merged together. It's a very simple rule. It's easy to draw. Didn't take me long. There we are. Simplification rules then. I know we've talked about simplification, but some of these are pretty cool. Select top 0 something from product. Not a query you write very often, but there is a simplification rule here for it. You can do this when you do select top 0 something into table to create an empty table with a particular structure. But if we just naively implemented this, you'd see a query plan something like this. So scan the clustered index, it wouldn't actually produce any rows. There's a top 0 operator after that. And that's perfectly fine. But there's a simplification rule called top on empty. You may not have written top 0, but there could be a part of your logical query tree. Maybe it's in a view that you weren't thinking about or something, that because of the parameters in your query actually is guaranteed to produce 0 rows. But anyway, this rule can replace that with that. Okay? And you'll see that sometimes. If you write something, a logical contradiction or something, you'll see your query plan. You know you made a mistake because you'll see a select from a constant scan. Won't touch any tables. And the advantage of that is a constant scan is just an in-memory structure with the same structure as from metadata as the table that you are accessing. So we don't have to take any locks, don't have to take any latches or anything else like that. It's just a little, very lightweight memory thing. Okay, top on empty. There's another one called gbagtbridge. These are those friends I was telling you about. This is my friend gbagtbridge. So group by aggregate to project. Again, this is all relational terminology. So group by aggregate, and we're going to turn it into a simple projection. So we have a query, name and sum of days to manufacture group by name. But name has a unique index on it. There is only one Highlander. So the group by and sum is logically redundant, right? If name is guaranteed to be unique, you don't need to do any group by because each row is already unique, to make the point over and over again. So a naive plan would look like that. Scan of the table, sorted into groups of name, and then do an aggregation on it. But there's no need, because of this information we have that's stored in the properties in the plan about what's key at what particular point in the plan, and what the functional dependencies are. So we can turn that gbag to a proj. And there's a proj. It's a project. Okay? Projecting a column. There's actually no need for that operator in the plan at all. It's architectural garbage that it stays there at all. It could be simply removed. And it doesn't do anything at all except something like define days to manufacture equals days to manufacture. It's a no-op. They could tidy it up, but they don't seem inclined to. Does that make sense? Yeah? And obviously we end up with a cheaper plan that way. We don't do a sort, we don't do a stream aggregate, just do a simple project, compute scalar. Same thing. Yes. Sorry?
You have here said that the name is unique.
Have I said that the name is unique? No, I have not said that, and I should. The names are unique. Yeah. Good on you, Klaus. You were rude to me earlier, so I'm not helping you. Yes, the name. I'll come on to where they're stored and where you can see them all a little bit later on. But yes, they have to be unique. Otherwise, well, who would know? Oh, I see what you're saying. I thought you meant the name of the rule. Oh, yes, you don't need the compute scalar. That's what I'm saying. It's just because at some point in the tree there was a sort and a stream aggregate, at least logically. This rule says to replace that combination in particular circumstances with a compute scalar, which it does. But there's nothing comes along later to say, oh, that's redundant. throw it away. It doesn't hurt the plan. It just looks messy. Okay? Sweet. So that's simplification rules, are just a couple of examples. There are lots of them, and we don't have time to look at pretty drawings of them all. But a simple exploration rule. So we're looking for new logical alternatives. We're looking to expand our search for things that are logically equivalent to what we were given from the parser and the binder and the algebraizer and whatever. So join commute is a simple one. It just says for inner join, relationally speaking, A join B is the same as B join A. Yeah? It's a relational identity. For inner join, those two things are the same. So join commute says, let's generate some alternatives and explore the space by moving those things around. So table A has moved, and they've all sort of moved around a little bit there, and the predicates have moved with them. So that's a new alternative. Mm-hmm. And joins are very good at producing alternatives. If you draw them all out, it very quickly gets very large, the number of ways you can rearrange inner joins. So there are a bunch of heuristics that it uses to limit that. It doesn't have the ability or the time or space to explore every possible join alternative, so it chooses some. Yes, sir. I'm going to go for a walk. My legs. Question on the previous slide. Oh.
The group by aggregates
Yep.
to project.
Yep.
So now in 2012, it has been replaced by group by aggregates to the project. I mean, basically the physical operator.
Help me out. Try it again.
In the previous slide,
Yeah.
you shown to me like say in the earlier rules, you have
I see.
like group by
Yeah.
group by to aggregate means like cluster index, then it starts and then
Okay.
do the group by.
I'm going to try and summarize that question as best I can. So I showed on the previous slide that query plan turning into that query plan. That's just me being helpful and illustrative. Yeah? That plan never really existed. That's what it would look like if gbag2proj didn't come along and do its thing. Okay? So I turned off gbag2proj to get that plan, but in the product you would never get it. You'd get that. It's just me trying to be helpful. Yes, sir.
We have two tables, one with like million rows, the other one is with like 1,000 rows.
Yeah.
Even then, would the order of the join would matter? Like if I do A join B or B join A?
Right, good question. So the question is, given two tables, one very much larger than the other, the order in which you join them doesn't really matter. It may do, depending on the algorithm that's physically chosen. So for nested loops, it certainly would. If you drive the loops from the million row table, you end up doing whatever's on the inner side a million times. You switch it around, it could be fewer. So yeah, even with hash join, you want the smaller input for the build table, so you use the minimum amount of memory. Yes, so there are physical implications to which way around the join goes. But it's a good question. Yeah. Okay. The second exploration rule, so new logical alternatives from existing trees I want to look at. Given our same exciting test query, so a basic plan, a basic execution plan based on the input tree we saw right at the beginning would just join the two tables together somehow, in this case using a nested loops, and then do a stream aggregate afterwards. But there's a rule called gbag before join, and you see that these names, I'm so glad they gave them descriptive names. I mean, they could have given them GUIDs or something, you know? And that would have made my life significantly harder. And, oh, by the way, I was introduced to the fact the other day that in the basic EULA for the product, it was you, wasn't it, Agen? You were saying, do not re-engineer this product? Yeah. Sorry about that. Yeah. I have no license to use SQL Server. I've broken it. Yeah, so gbag before join wants to move a group by aggregate before the join, lower down the tree. Yeah? So we go from that, with the stream aggregates after the join, to that where it's pushed it below the merge join. And in this particular case, the costing comes out with the this version that's on screen now being marginally cheaper than the other one. The optimizer works out that although it's a scan of the table and grouping everything up front by product ID on all the quantities from the product inventory table, because it then gives it a sorted stream that it can just throw into a merge join, it works out that that is marginally cheaper than finding all the products nested loops into transaction history, and then summing each row per group. Yeah? I mean, if we had to rewrite our queries to do that sort of thing all the time, yeah, life would very quickly get tedious. So it's great that these little things exist, I think. So it considers all these things, costs them, and then chooses the one that looks best. Okay. 3. Not all rules are simple. These are pretty good. This is my good friend. Cell sucrage to any egg, and GBEgg to sort. Cell sucrage to any egg is actually something I've written a blog post about, the undocumented any aggregate. So the query there that I'm not going to describe in detail because I am running way behind is basically saying give me one member per group. I don't care which member, I want any member per group. It's a fair enough sort of query that you write sometimes. You say, I've got a group, just give me any member, I want to get a feel for what's there. So quite often you'll write a row number query, partition it by, so what I'm doing here is on the inventory table, for a shelf and a bin in the warehouse, just give me any product, I don't care which one. So I've written a subquery that numbers the rows, partitioned by shelf and bin, and also ordered by shelf and bin, and then just said where row number is 1. If you think about it logically, that could give me any row, because they'll all have number 1. Okay. Now, without this rule, we seek on product identity, do a sort, a segment to set the group boundaries, sequence project to do the row number, and then we filter it out where row number is 1. But cell sucrage on any egg is smart enough to say what you're actually doing there is saying do a distinct sort per group and just give me any one that you come across. Now, I need to turn off GBEgg to sort to get you the inside plan that I want to show you. Before it became that nice green-framed final result, that's what it actually is. A sort and a stream aggregate can sometimes be combined into a distinct sort. But in the execution plan, the properties that show you this interesting aggregate disappear. But if you hover over the stream aggregate in the execution plan, you will see the use of this internal-only aggregate, any. It's like min, max, avg, sum, but it says any. And it will give you any one that it comes across for a particular group. We can't write it directly, but you can use this pattern with row number and 1, and this rule will kick in, and instead of a complex, expensive plan like that, you get a nice, simple final plan like that. Okay. I was going to do a demo on... What time are we finishing today? Is it 4:30? 4. Okay. So segment top is really interesting, and it's my first ever blog entry. I suggest, please go read it. I would like to demo it, but I have nowhere near enough time. I'm sorry. So, talk about implementation rules. These turn a logical alternative into a physical reality. Examples are jun to null, jun to hush, and jun to sum. Join to nested loops, join to hash join, and join to sort merge. So take a logical join and produce 3 alternatives. There are 2 more for GBEgg in the current product, stream aggregate and hash aggregate, GBEgg to strum, and GBEgg to hush. There's select to filter, get to scan, get index to range. There are loads of these, and I'm not going to go through them all, but you get the idea, right? They turn logical parts of the query tree into a physical implementation. Now, in a lot of these demos so far, I've turned off certain rules to show you what the intermediate stage would look like, and it is good to experiment with and gives you a feel for how these things work. And when you don't get the query plan you wanted, it's perhaps because a particular rule didn't fire when you thought it would. Now, when you use join hints or when you use query hints, what you are effectively doing is turning off a certain set of these implementation rules typically. So a loop join hint will turn off the hash and merge implementation rules, and so on and so forth. There's also a couple of undocumented alternatives. You can use dbcc rule off and rule on to turn a particular named rule or numbered rule on or off for a session. Anyway, if you Bing or Google that, you can find the details, and also query rule off that I've used in some of the demos earlier. Okay, now a quick demo here of a script I used to show very quickly which rules were actually used in optimizing a query. So this is demo 7. Usual preamble. It's a script, and it uses the undocumented DMV, sysdm exec query transformation stats, which shows for each rule some statistics about it. So I create a couple of tables and basically take a snapshot of this table, run my test query, and then see what changed. So easiest to show you just by running the whole thing. So for our test query, these are the results. The names of the rules, my dear friends, are down the left-hand side. These are the rules that matched and produced an intermediate result in optimizing this query. And there were 21 rules out of the 397 that participated to give us our final fully optimized plan that we saw right at the start. And this final fully optimized thing took no time at all to optimize. It was lightning fast, I'm sure you noticed, and a final cost of 0.029. So 3/100ths of a cost unit, of an arbitrary cost unit. Now, what we can do for fun, and I would do this one by one if I had more time, was to turn off these rules individually and see what effect it has on the plan and what it does with the cost. Now I'm just going to do one. I'm going to turn off GBAG before join. So this is the one that considers performing an aggregate before a join. Okay. So now we only have 19 rules applied, because obviously when you apply one rule, you get an alternative, and a new rule might come along, look at that alternative, and generate a new one. So there's a sort of cascading. See where the name Cascades came from? Yeah. So now we get a query plan without the aggregate before the join, and that was on previous slides. One more, because it's fun. But the cost went up slightly. It went up from 0.029 to 0.035. Now we've only got 20 rules. And a slightly different plan with an explicit sort. And if I turn them all off, so join to sort merge, index to range, select on join, we saw earlier, building a spool, join commute, we saw that one earlier. A join B is the same as B join A. Only 4 rules in this particular case. So it took my query, and I've really hurt the optimizer by limiting what it can do, but it managed to find a plan by only running 4 rules. And it came up with this. So it's taken the 2 tables, it's doing a Cartesian product, hence the big red warning cross. A filter after the... This is the original logical tree we saw right at the beginning. Yeah. The two gets, the Cartesian, the filter, GBAG, project, that's, yeah. If you hurt the optimizer, it will come up with a plan, but you won't like it. And finally, if I turn off one of some rules are required, and if I turn off a required rule, select a filter, in this particular case, I know it's required. Query processor could not produce a query plan because of the hints defined in this query. Yeah? Yeah, I pushed it way too far. All right. And the final cost there with the Cartesian product plan was 3.65 cost units. So that is 100 times worse than we started with. But anyway, messing about with that, the scripts are available. Please do try it if you're feeling brave. On a test system, it can give you a real insight into how this is working internally. And it's not just academic and geeky and stuff, although it is, right? It can give you a feel for, when you write a query, what sort of query plan to expect. And if you don't get that query plan, what you might do to perhaps rewrite or help the optimizer to get its act together. All right. You notice I'm picking up the pace somewhat. I greatly overestimated this. All right. So, generating all these alternatives, it needs somewhere to keep them. Okay? And in Cascades, it uses a structure called the memo. Okay? I call it memo. It could be memo. I don't know. I say memo where I come from. Do you say memo or memo? Memo, of course. Everyone says memo. Okay, so in the memo structure, initially you start off, it's a direct copy from the input tree, so you just end up with one group per node, storage stored in the memo. And the memo is just a way of keeping track of alternatives and not generating duplicates and things like that. So each group in the memo will have the same logical properties, because each group is a logical thing that we're trying to find alternatives for. But they may well have, and generally will have, different physical properties which we can cost and choose between. A little bit more to it than that, but that's essentially the message I want to get across. So for our test query, the initial memo tree looks like this. And there's a trace flag to show you this, which I'm going to skip over. But again, it's another tree representation internally. It's a group by at the top of the tree, a join, project list, select, compare. Okay, that's what the memo looks like at the start of cost-based optimization. Now, I mentioned that cost-based optimization is expensive to get into because that's when it loads all the metadata, all the statistics. It has to set up the memo, copy it in. It's a reasonably complex structure, and it's going to get more complex quickly. So all those things are startup costs which Trivial Plan avoids, okay? All right. I have a demo for this, which I'm going to skip over. It's just a trace flag. I think it's 8607 then? 6? One of the two. It's in the script, but it will show you that tree that I just showed on the screen. Are you happy for me to skip that? Yeah, thanks, guys. So, optimization proceeds in phases. It doesn't do everything all at once. The idea is that simple or OLTP, perhaps, type queries will need a different strategy from very complex data warehouse ones. So, if it matches the conditions for a particular phase, it'll start off with a phase called search 0, because geeks always start numbering at 0. I don't. It drives me nuts. Numbers start at 1, right, if you're human? Yeah? Jeez. And the first search is called, also has a name, transaction processing. It's primarily nested loops join. If it can't find a nested loops join solution, it may use a hash. But generally speaking, this is for simple navigational OLTP type queries. Only some of the available rules are enabled for the optimizer to find alternatives. And it requires a minimum of 3 tables to enter this phase. So if your query only has 2 tables in it, it won't qualify for transaction processing. You need at least 3. Thank you, Ben, for that. You mentioned that on your blog many years ago, and it led me to work out why that's the case. Search 1 is the next phase. So search 0 may find a plan, and if it's good enough, it will stop there, and it will get executed, and life's good. If it enters search 0, it may find a plan that's pretty expensive based on nested loops, so it will go on to search 1. Search 1 is another rerun of this exploration implementation idea, so you find new alternatives, cost them, put them in the memo. And search 1, all the transformation rules are available. Not all the rules in general, but all the transformation rules are available. It does a little bit of join reordering as well. And it can run twice. It can run once, and then it can run once again with parallelism as a requirement. Okay, so it'll try to generate a search 1 serial plan first of all, get a cost for that. If that's still pretty high, it'll run search 1 again with a requirement to produce a parallel plan. And at the end of that, it'll look at the parallel plan and the serial plan, and whichever one was cheaper, it'll choose. And it might then go into search 2, which is full optimization. Yeah, and like everything, all bets are off with this one. It can take quite a long time. Not many queries will qualify for search 2. Most of your queries in general workloads will go through search 1, serial or parallel. If you're OLTP, you may get a lot of search 0 queries. But in general, search 1 is where most of your queries will end up. Search 2 takes the decision from search 1. If it was a serial plan, then search 2 only searches for serial plans. If it was a parallel plan, it only does more searching on parallel plans. All right, so search 1 is really the key in a lot of cases. And then finally, once all this exploration, implementation, and costing is complete, it copies the memo structure out of memory into a form that the query executor can actually execute. And it performs a few final small rewrites. It can add static bitmap filters to parallel hash join and merge join plans. It can push non-saggable predicates down towards the leaves. We saw that earlier. It doesn't actually happen as part of optimization. The optimizer tree comes out with those filters in place, and the filters get pushed down into the scanner seekers as a late phase rewrite optimization. Okay. Yes, sir.
So joins prevent trivial plan, correct?
Yep.
So if you have a join, just a query of 2 tables, so it's not trivial, but it doesn't enter search 0, so is there kind of this search negative 1 then?
Okay, so the question was that joins prevent a trivial plan. So if you only have 2 tables that don't go into search 0, and it goes into search 1,
Well, it can't go into,
it can't go into search 0, no, because, yep.
it requires 3 tables.
Yep.
Is there kind of this gray area between trivial and search 0 that,
I guess there is.
yeah.
I guess there is. I mean, it seems to have developed over the years. I mean, they first put the cost-based optimizer thing in, and because they saw some worse performance than on 6.5 and 7 with certain class of queries. So trivial plan got beefed up, and then Search Zero was put in as another optimization. But I guess the thinking is that on true navigational queries, you have three tables. So, yeah. Okay, so the optimization phases I'm talking about. Each phase, Search 0, Search 1, Search 1 with parallel, and Search 2, is a round of applying exploration rules to generate more alternatives to store in the memo. So we've got lots of new logical alternatives to choose from. A round of implementation rules to turn each of those into a physical alternative. And each phase has entry conditions, as I sort of mentioned about the three-table thing, a set of rules that it can use, and conditions to terminate. So search can terminate early for a couple of... It can search early if the optimizer detects that it's found a really good plan already, and it's not really worth going on and searching. So in the F4 window, you'll see an early termination reason of good enough plan found. Yeah, so it gets so far through a stage, says, wow, that's awesome, that's great, that's good enough, and away we go. Its goal is a good plan quickly, not exhaustive search. It also sets a budget for each search phase based on the cost that came out of the previous stage. So if the previous stage came out with a cost of, say, 100, it'll set itself a budget of the number of rules it can apply, the number of alternatives to look at, and if it exceeds that, you'll get a timeout. Now, timeout doesn't necessarily mean anything bad happened. It's just a protection measure to avoid optimization getting out of control. Yeah? You don't want to sit there for 30 minutes while it churns through join alternatives. So there are heuristics all over the product that say, you know, we won't explore all alternatives because it's already above a cost of a cheaper one I found earlier. This is the benefit of the memo. You can quickly check to see if you found something similar earlier that was cheaper. So it has a lot of heuristic stuff in there to say, let's keep focused on the main optimization task. So it prevents exhaustive search that way. All right. And in show plans, I showed you earlier with my beautiful blue rectangles, it only shows trivial or full. Now full means either search 0, search 1, search 1 parallel, search 2. It doesn't distinguish. You need there's a DMV here, SysDM exec query optimizer info, that keeps a running total of how many trivial search 0, search 1, search 2, and it does have that labels for the counter, so you can take a snapshot, run your query, look at the snapshot again, do some math, or you can use a trace flag. And I'm very quickly going to demo this. Hey, I'm sure I've got until 4:15, right? Sure. Yeah, well, it should be, but I lost 15 minutes in the break, so that's yeah, I'm on New Zealand time. Hey, we've got all day. Well, 21 hours. All right, so very quickly, this is the DMV I was talking about, SysDM exec query optimizer info. There's a whole bunch of counters in there, but here they are: trivial plan, search 0, search 1, search 2. This stuff is real, people. And you can see search 1 is by far and away the most popular. Right? Only 14 times have I gone to search 2, and that's because I deliberately wrote a query to do so. All right. So here's an example of a search 0 transaction processing query, and more magic trace flags. 8606, so I can look at the tree. We saw that one earlier. And 8675, again, you know, it's almost documented now. It's on so many blogs and books and things. To show me which stages were entered. So I'll just run that very quickly. There's the results. And on the messages tab, we have the tree that we saw earlier. And here at the end, you see, oh my goodness. So 91 tasks. So each time it does an exploration or an implementation or something, that's a task. So it did 91 things. It came out of search 0 and didn't go on any further, so it found a good enough plan in search 0. Make sense? Well, it's just text, isn't it? So, and here's an example of a query that doesn't qualify for search 0 because it's only got 2 tables. Goes into search 1, some results. In search 1, 216 moves or tasks were made, and it's exploration activities. Yep.
asking about, not qualifying for search 0. Is it often then going to go straight to search 1 and search under that?
Yes, the question was skipping search 0, will it go straight to search 1 and play with that directly? Yes, that's exactly what it does. So most queries go straight to search 1. Okay. Why would it go to a more expensive search phase just because of the number of tables? My understanding of this is that the search 0 is a specific optimization for OOTP queries that tend to have 3 or more tables, and the navigational strategy is going to be the best for them. So it only has the rules, it doesn't do much reordering, it just does nested loops. It wouldn't be a good win for most queries. Okay. So this particular query here, you can see, I hope you can read that. It went into search 0 because it had 3 tables, didn't find a good enough plan. Went into search 1, didn't find a good enough serial plan. Did search 1 again with parallelism as a requirement. And in the end, it found a plan which is parallel, and it found was good enough. Okay. And I've got more examples there of timing out in search 0. There's a trace flag to only go into phase 2. But there's one interesting one I want to do here, and it involves the cost threshold for parallelism again. I'm going to set it to 0 like a crazy man, like I did earlier. All right. Remember, that means we can't get a trivial plan anymore. And now I'm going to do select star from production.product. That query, I'm going to optimize it with our trace flag on. Okay, we've got a timeout. All right. Now, the reason we've got a timeout is because the budgeted cost for optimizing that query in full optimization was so low that it couldn't even complete 15 tasks. Yeah. So you've got a timeout. So timeouts aren't always bad. Yeah. It just means that it met a limit that it thought was sensible for the query. I just wanted to show you a timeout there on select star from a table. Yeah. The optimizer timed out. It doesn't mean it's rubbish. I'm sorry, I didn't hear that. Does SQL Server log anything in log when it times out? No, but that counter in that DMV I mentioned, there's one for timeouts. Yeah. Okay. Anyway, that's the one I wanted to show you on phases. So costing runs after each round of implementation rules, finds all the physical alternatives, and chooses the cheapest one. It's all based on a model and heuristics and stuff, and it's amazing, really, that this general framework for all the different databases you guys have, all the different designs, all the different quantities, produces a reasonable plan in most circumstances for most queries. I think that's a heck of a challenge. If I send you out to write a general-purpose optimizer that takes any general T-SQL as an input and produces an execution plan that the query executor can run, you have to write a general thing that works well for everyone in the world. I think that's pretty amazing. So there are some limitations. There's a lot of simplifying assumptions, like each execution starts with a cold buffer pool, which tends to mean that the optimizer overcosts the importance of logical I/O. It assumes that at least one page is going to have to come from the disk each time, and it assumes that seeks are going to be randomly distributed. So if your data is different, then its model may not work so well. There's also an argument to say that some of the magic numbers it uses could be updated. For example, there's a fixed ratio in there that says 320 seeks is about the same cost as scanning 1,350 pages. It may have been true at some point in the past. It's not true any longer. Probably not on your hardware, and definitely not on SSDs and Fusion I/O and things like that. And that makes some people cross. So there are reasons, conservative reasons, why it uses this model to overcost physical I/O and to make random I/O much more extensive than sequential, because the cost of getting that wrong is much worse. It's not so bad as getting it right. So if you produce a plan on the basis that it does a scan, it's not going to be massively worse. But if you did the other way around and assumed that they were roughly the same cost and did lots of iterative plans, it could quickly produce a very bad plan that would hurt a lot of people. Okay. So after all this exploration and implementation and whatever, we end up with a final memo structure with all the alternatives in it. I'm going to skip that as well. Sorry. But I do want to talk about this. No, I'm not. I'm going to show you that. You need to see it. We should have a vote, eh? And besides, it's demo 10 of 10, so it looks like I've actually finished on time, right? Yeah, let's go with that. All right. So our test query, after all said and done, there's always a trace flag. This one's 8615. So we get our results, and we have a final memo structure which shows you in each group a logical alternative and a physical one. Now you won't see all the alternatives that it considers because it does quite aggressive pruning to stop alternatives getting out of hand. As I mentioned very quickly earlier, if it starts looking at an alternative and can quickly see that it's obviously more expensive than something it's searched before, it just throws it away, prunes it out and doesn't bother. And that's quite aggressive. So by the end, where's the one I want? Yeah, so each group came from a node in the logical tree, remember? And new nodes can get created and things like that. But here on group 13, for example, it shows you two physical alternatives it considered. It considered an apply, which is nested loops, correlated join, or it considered a merge join, one-to-many join type inner. There's all sorts of fascinating details there. But you can see from the numbers, 0, 1, 7, 9, things have been pruned out and thrown away. Okay. Well, I just want to show you that exists. And finally, there's just one last magic flag, 8607, which produces the final output tree from the optimizer. There's still some little rewrites that go into this, as I mentioned earlier, but it gives you something that looks quite a bit like an execution plan. All right, kids, we're nearly there. I mentioned the push non-cyclable predicates earlier. This is a very dangerous pattern I see quite a lot, and I wanted to mention it. So select product ID name from product where color equals multi. There's no index to support that, so we end up with a clustered index scan with a residual predicate doing the filtering on color equals multi. Yeah? You've all seen that in plans, right? What actually comes out of the optimizer is that. Yeah? And this late phase push non-cyclable predicate thing rewrites it into that. Okay? Now, I've mentioned that, so you know it and you're fully aware of it. But I have seen people rewrite their queries. Yeah? Say, well, our company policy is that we need seeks. Yeah? Scans are bad, seeks are good. So they do something like this, yeah? For which physical pain should be the penalty. So they search. Do you know? So hanging's too good for them, that sort of thing. So product ID is an integer, so they're just greater than equal int min and less than equal int max. And look, yay, it's a seek. Awesome. But if we use that 9130 flag to stop it pushing this non-cyclable predicate, we can see. Hey, let's do that again. Yay. We can see that 504 rows, the whole table, it's not a very big table, but I could have used a bigger one to make it more dramatic, I suppose. But so the seek just returns all the rows in the table, obviously. And then you have this filter. I mean, it's a ridiculous thing to do. And you've achieved less than nothing. It's more expensive than just doing the original thing. And so if you see anyone doing that, just, I don't know, hit them. Educate them, I mean. Yeah. Index intersection. It's just one little thing I want to mention. So the optimizer does have the ability to, if you don't have a perfect covering index for a query, it can look at using two indexes and choosing the intersection. As an example, this isn't considered less hindered. Okay, all right. I'll come back to that. From product, where product ID is 1 or the name is Racing Socks Medium. Yeah. Now I have an index on product ID and I have an index on name, but I don't. There's an or there. So the default plan we get is an index scan, which has a residual predicate looking for that or clause. But if I use a force seek hint, and you do need to hint to get index intersection, it doesn't routinely consider this, it's just too expensive to do. With a force seek hint, I wasn't sure that was going to work. Two index seeks, one for the socks, one for product ID 1, merges them together and does a distinct as is semantically required. And in some cases that may be faster or not. But yeah, if you ever see a plan you wonder why the optimizer didn't do an index intersection, it's because it doesn't unless you force it to, either with four seek's a good one, or a named index hint, or two named index hints. All good. And this is the one we saw early on, combining transformation rules together, but it's quite a nice animated slide which I want to share with you. This is the distinct on the left join. So a distinct on the left join where we're rejecting nulls on the quantity column. So a naive plan would be a left outer join, filter, sort, and stream aggregate. We apply simplify LOJN, login. Simplify login is a simplification rule that comes along, and it turns a left outer join with null reduction into a join, and GBAG to sort turns group by aggregate into a distinct sort as we sort earlier. So that makes it a lot simpler, right? So we've turned our outer join into an inner join, and then we've got just a sort, distinct sort at the end. But GBAG to listen comes along. Group by aggregate on a join, yeah? Group by aggregate above a join, which is what we've got, to left semi-join. Yeah? And I'm mentioning this just so if you look at some of the rules, some of the abbreviations make some sense to you. LSJN is left semi-join. So applying that join, that's how that query ends up being a simple hash match right semi-join. Okay? It says left semi-join, but there's another rule that comes along and says, hey, would that be more efficient the other way around? It's a bit like join commute. Yeah, so we end up with a right. There isn't a rule for GBAG to, I'm not even going to try. Okay, and it's exactly the same as if we'd written the query with exists. Yeah, so a secondary goal of the optimizer is to allow you to write your query, with some freedom for syntax that you find natural and still get an awesome plan. All right. It turns out that writing it the exists way is more natural to me and takes the optimizer less effort to get to a good plan for. So you could argue it's superior. I would argue it's superior. But yeah, there we go. I have 2 minutes. So, row goals. When you have a top or a fast or an exist clause or something like that, what you're saying is the entire subquery doesn't need to run, you just need a few rows from it. So costing works in a slightly different way. Instead of costing the whole plan as if all the results are going to be returned, it does a default costing. Then it does some math. So I've added a top 50. So it does 50 times the cardinality before, divided by expected cardinality. The top operator goes in, the cardinalities are adjusted, and the costing's adjusted. So it's a very powerful technique for the optimizer to reason about finding the first n rows quickly. It actually goes down the tree, adjusting all the cost estimates based on this row goal target. Last thing to mention, I mentioned that the memo didn't contain all the alternatives because they got pruned out. But if you use plan forcing, this makes the optimizer work in a slightly different way. It turns off this pruning heuristic. It uses the shape of the XML to guide its search towards the plan you've asked for. It doesn't literally say, this is the plan, execute it. The XML is not a plan. Okay? It is a representation of a description of an image of a plan. So it takes the shape of that plan, and it uses that to guide the search instead of just applying rules and looking at cost goals and pruning aggressively. So it doesn't prune at all. So on that little screenshot there, you can see there are probably 12 different physical alternatives operating on other groups. So that's one way to get to see more physical alternatives in the final memo. Okay, I think I'm pretty much out of time, which is a shame because I was enjoying that. So I'll flip to the path is awesome slide, and they do awesome stuff, and you should get involved in it all, and do something to give back to the community as well, apart from paying to come to an expensive but great conference. And thank you for coming today. If you guys come to New Zealand, we'll talk about it all day. Turn the mic off.